நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் மதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே. வந்தே மாதரம் வந்தே மாதரம் சுஜலாம் சுஃபலாம் மலயஜ ஷீதலாம் சஸ்யஷ்யாமலாம் மாதரம் வந்தே மாதரம் शुभ्रज्योत्स्नां पुलकितयामिनीं फुल्लकुसुमितद्रुमदलशोभिनी
I see transactions. Naviki to give us plenary address.
Hi, good morning, everyone.
Thank you very much for the
Introduction.
I think I'm waiting for the controller for my presentation. So,
Controller. Okay.
ஏன் இப்போ ஸ்டார்டிங்ல ப்ரிப்பேர் தான் செக் பண்ண முடியும் ஏன் மேம் முன்னாடி நான் செக் பண்ண
Check பண்ணிட்டேன் sir.
அப்புறம் ஏன் வரையும்
Okay. Good afternoon.
Okay, so
நான் மாட்ட முடியும்.
இப்போ வந்துச்சு Thank you again for coming to our introduction. Still good நினைக்கிறேன் my staff such that I can keep up the schedule.
okay, so before I start, I'd like to express my sincere thanks to Professor Deepa Venkatesh for inviting me to such a great event like this. And I'm very pleased and honored to be here, sharing with you our perspective on the R&D of optical networking from the past, present, and to the future, which is actually indeed quite a journey to the next generation green digital infrastructure. And I'd like to express my many congratulations to all of you for the inauguration of such a great, important, the national project as Advanced Optical Communication Testbed.
Kavi.
Okay, so let me begin with a slide which is very commonly cited for everyone whenever you speak about how important photonics is. Right, so I don't need to explain. I mean, I need to explain about the all of these graphs shown in this view graph because I believe that we already share the value of the photonics and the importance of the photonics because we have to cope with the exponential growth of the data, the connections throughout the world. And so the exponential growth is, that all matters. And just saying exponential growth is easy. However, for us, the photonics engineers and the researchers, to really realize the exponential, sustain the exponential growth of the photonics technology is really hard. So it takes, really a continuous efforts year by year and decade by decade. We have to be really keep being creative and create the innovative technologies so consecutively over decades. And so far, we have been working so hard, and optical fiber communication was first commercialized in early 80s, right? And then at that time, the capacity per fiber was only less than 100 megabit per second. And then, because the optical fiber communication is to exploit the physical properties of electromagnetic wave for carrying information to remote places. So in the first stage, we have exploited the time resource about the electromagnetic field to increase the amount of the data to be transferred. And then we, with the very innovative, device technology, which is the optical amplification. And because this operates in a very broad band, so it comes with the wavelength division multiplexing, exploiting the the resource of the wavelengths of the electromagnetic wave. In so doing, we've been keep increasing exponentially the capacity per fiber at almost the same pace as the Moore's law. And then digital coherent technology came along, and which enabled to exploit the properties of phase and amplitude of electromagnetic wave for increased capacity of optical fiber communications, as well as of states of polarization. And then, we have, depleted all the available physical properties of electromagnetic wave. And then now we are resorting to, exploit the resources of space modes for increasing the capacity further for the future. So, however, in so doing, however, in so doing, we have been reaching the fundamental limits about optical networking. Of course, we are, a few dB close to the so-called nonlinear channel limit. And also, if you look at the computing, we are witnessing the slowing down and eventually demise of the Moore's law. So, given this, having reached the fundamental limits, if you want to further scale, and then that is actually further demanded, if you look at the foreseeable future, we still need this exponential growth going. And like if you look at the data center traffic, it's really increasing exponentially. And the amount of the data exchanged inside the data center is several times as large as that of internet. And also we have a great expectation towards the IoT technologies. And also recently, the quite surging interest emerging, with the large language model of the AI technology. So everything, we really need to create further more technologies, enabling the further exponential growth of the data processed on the digital infrastructure for the decades to come. So, given having achieved the fundamental limits, what does try to increasing the information means? So, the end of the Moore's law means the more energy to be consumed with increasing information. So here we hear the photonics people get together and then create some the smart idea how we can defy the fundamental limits or get around the fundamental limits, allowing us to further scale the data capacity. So how does the end of Moore's law sound to you? And if you look at the saying by Gordon Moore, he said, the nature of exponential is that you push them out and eventually disaster happens. And this seems to be exactly what's happening to Intel now. And on the other hand, if you look at the saying by the computer scientists, they say it's really a new golden age for computer architecture. And it seems to be actually what is happening to NVIDIA these days, make use of great accelerators and let the system further scaling. And then what's the role of the photonics in this context? And here's a famous wisdom passed by the Bell Labs. It says, if you find yourself fighting with silicon, then don't. we actually have a lot of lessons learned in the past. So we have to be really careful and think hard, what really makes sense out of new photonic technologies. And also we have to ask ourselves, how does this wisdom apply to the world after the end of the Moore's law? So here comes our story, and I'd like to start with asking ourselves where we are heading actually. And one of the clue can be found in the Japan's view, and the Japanese government actually envisions the so-called Society 5.0. That's Japan's future vision about the digital infrastructure. But what they are saying is nothing unique or nothing special. I think it applies to everyone all over the world, because that's the only high-speed and automated cyber physical systems. So conventionally, if you define the present society is 4.0, we have a very nice cloud system out there, and we have a nice smartphone and very easy to get access to the cloud. However, if you want to really, utilize the full potential of what is stored in the cloud, you really have to work hard, and everything you have to do almost manually. You have to search manually, and you have to collect the data manually, and then you have to sort it out, and then you have to build your own database or any of the set of the data available for your own big data analysis, and everything you have to do, sort of manually. So that's the world of the current information society. And on the other hand, Society 5.0 is aiming at the world, everything is automatic. So you have a lot of sensors in the physical space deployed, and automatically all the data, whatever the data is collected automatically to the cyberspace. And then cyberspace is supposed to automatically, utilize those collected data to create a digital twin in the cyberspace, the digital twin of the physical space in the cyberspace. And with this, digital twin or dynamic map or whatever you call the big data analysis or AI analysis are going to be done in a sort of automatic manner. And then you find some sort of a potential problems or any of the, the needs, they're going to, proactively offer some sort of a solutions or countermeasures or informations to fed back to the physical space in an automatic manner. So in so doing, you can do this sort of, positive, feedback cycles. That's they are talking about as a Society 5.0. So this is sort of a dreamy kind of vision, but I think the world, we really want to this kind of situation. And in order to do that, we really need to increase the information capacity of the network, right? So especially, if we think, the interface between the physical and the cyberspaces is going to be more and more important. And that exactly, envisioned by the, the standardization of 5G, 6G, and beyond. And if you look at the specs of the 5G, they are really demanding if you are, optical engineers. And for example, those are listed in here. And if you try to achieve all of these demanding requirements, the optical network infrastructure has to be about 1,000 times as high, large capacity as the present infrastructure. And the 6G is even more advanced. And so if you try to achieve 100% of the requirements all the time, and then you're going to need more than 10 times as large capacity as the present the infrastructure. This doesn't make sense given the fundamental limits, because you really have to increase the energy consumption by 1,000 or 10,000 times, and this is not sustainable at all. So here we photonics community have to come up with something very good solutions with cutting edge technologies. But in order to do that, we really need sort of a strategy how we can define the fundamental limits or detouring, the circumvent the fundamental limits. Okay, but if you look at the specs, derived in the 5G or 6G, of course, that, they don't really mean that the network infrastructure, have to achieve their requirements 100% uniformly all the time. But because the requirements is, the system service requirements is going to be extremely diverse in the world after the 5G and 6G. So the network, each, the very diverse applications, each of these applications requires, different specs for the networks. So you have to, the network then have to be very flexible and so flexible as to be very efficient as a total. So in this context, the network infrastructure has to be, so to say, softwareized. So everything, have to be, defined on the software domain. So the clarification is going to be key, and that this, the clarification is only feasible on the hardware platform of a very, powerful but very low cost. So, and those hardware has to be, flexible on the software domain. So the virtualization, the network virtualization is going to be very important, and the hardware has to be white box as much as possible in order to make things, the reasonable, it's inexpensive in terms of cost benefit, and this, direction has already been set by HC and ORAN alliances in the mobile network. So they define the concept of mobile edge computing. On top of it, they can, construct in the software manner. I mean, define the various kinds of network slices simultaneously, operatable on the same common hardware platform. So, well, in this platform, apparently, you really need a sort of a generic, hardware white box server, environment. And so if you want to realize all of the networking function at software level, and then, the more compute performance is going to be necessary. However, we are facing the slowing down of the Moore's law. And so the post-Moore's law has already been entered. And, this is, well, I think I don't need to explain in detail, but, because the free lunch is over due to the end of the Moore's law, the general purpose CPUs won't scale any longer. But as you can see on your right side bottom graph, the TPU or DPU or GPU, the special purpose engines are, has, more performances, orders of magnitude better than just the general purpose CPUs. So the key is going to be how we can make use of those, special purpose engines. And so the higher performance can only be achieved by the specialization and heterogeneity of accelerators. But that would sacrifice the versatility and high utilization of hardware, which is, of course, something that we have to avoid. And therefore, the concept of disaggregation and reconfiguration or composable disaggregation infrastructure would become very important. And on top of this kind of platform, because the data are generated everywhere and then processed everywhere, and we have to be aware of how you can handle efficiently the data or memory in the context of in this context, and so we really need to achieve the usability and capability to all about the agile CPU offloading. And this one, thank you, actually, sounds nice and very sensible to go, further scaling the overall systems beyond the demise of the Moore's law. However, if you think, hard about the system, and then you realize that, they're just shifting the issues from computing itself to the network. So the photonics people, we are now receiving the very challenging issues from the computing in order to, realize this sort of the concept of the new computer architecture. So we need ever more powerful interconnect and with the high bandwidth, low latency, low energy, and high security. So here comes the photonics people, have to think, how can we make use of optical networking technology inside computing? So let us step back and take a bird's eye view on the historical evolution of optical networking. So here's the graph shows the vertical axis capacity of data transfer against the horizontal axis distance. And so the society needs is increasing for the increasing capacity of the data transfer, right? So as time goes by, the society needs is going to from the bottom to moving up to upward. And in the very beginning, let's see. Sorry. Okay. So the optical communication was invented and the first applied to telephone network in the early 80s. But, back then, that was the fiber capacity per fiber was up to, per channel was up to 40 G. So here's, depending on the distance, there is a division line between which you want to preferably go with electrical signals or you want to convert to an optical signal. That is 100 gigabit per second times the meter, famous sort of empirical line. And so the optical technology was only applied to a long, wide area networks back then. However, the hyperscaler came along and they built a huge, hyperscale data centers in which a huge amount of the data has to be exchanged. And so the photonics has began to be, applied to, widely applied to the data communications because of the, advent of the hyperscalers. And then now, as I explained, now we are entering the era of photonics electronics convergence, where, photonic technology is going to be applied to the interconnect inside compute. So the enabling technology is going to be, the integration, right? And so the silicon photonics or co-packaging of the photonic devices and electronic devices. And also, as I explained, disaggregation or virtualization or automation kind of, engineering or software technology has to be co-designed together with the hardware. And then combining these and as a whole, you can have the new technology or paradigm shifting so-called photonics electronics convergence. And then afterwards, I'm going to explain a little bit later, but maybe, further leap enabled by photonics, that would be a, sort of a wish list of our photonics people. So in this context, OE-EO conversion efficiency in terms of a picojoule per bit is very important. And here on your left-hand side, I plotted the energy per bit of a client 100G and a client coherent 100G. And both are, improving year by year at almost the same pace as the Moore's law. And they are approaching to the 10 picojoule per bit within a year, or it has been already achieved in the technology-wise. And so it's going to be comparable. The 10 picojoule per bit is about the energy efficiency of the memory, the DRAM memory like GDDR. So what does it mean? The converting electrical signal to optical signal will only take the same energy as that the DRAM would take. So you can, easily replace the DRAM with the optical transceiver on it, and the still system doesn't hurt much because the energy consumption is very comparable. But on the other hand, if you look at, let me go back. So on the other hand, if you look at the switch ASIC, the picojoule per bit trend here, and because the switch is, it's two-dimensional, so it scales, the number of transistors scales quadratically with the throughput, right? So again, the switch ASIC doesn't, improve as good as well as the optical transceivers. So on your right-hand side, if you look at the energy consumption of the switch ASIC, the year by year, the data center is increasing the capacity, but the energy consumption is increasing accordingly. And now the switch ASIC, one single chip consumes nearly 800 watts, which is already beyond the air cooling limit. So system is at the brink of the limit already. So that's the reason why the co-packaged optics is attracting a lot of attention these days. So the co-packaged optics is to eliminate the electrical wiring between the LSI and front panel pluggable modules. By doing so, well, you can save the energy consumed by the electrical wiring. And as the bandwidth gets growing, and then the more the energy has to be consumed there. So again, back to the 100G times meter division line. So we really need to do something about this electrical wiring on board or inside the compute. So here comes the silicon photonics and enabling the converting the golden box into just a small single chip, right, and an integratable chip. So it enables to co-package with the LSI and the transceiver by virtue of the high integration feature of silicon photonics. And so this successfully you can eliminate the energy consuming electric wiring on board. And once the electrical signal is converted to optical signal, the optical signal is almost free to propagate at any distances, right? So everything is going to work better in terms of electrical energy consumption and also performance as well. So I don't think I need to go into detail about the silicon photonics because I assume that everyone is very familiar with silicon photonics. So that will, but anyway, in this context, silicon photonics becomes a very, very important technology. Mostly because of its miniaturization feature, and because the size is very small. It can be very energy saving as well. But of course, the silicon basically, has a physical property not so great, the mobility in terms of electrons. So we have to do something furthermore. But anyway, miniaturizing everything will always contribute to energy savings. So silicon photonics is going to be a very important platform for the optoelectronic device for the future. And so the co-packaged optics is really, needed by hyperscalers in the Northern America. And so the Meta and Microsoft has already been leading the standardization at the OIF, Optical Internet Networking Forum. And some of the vendors have already, did sort of live demonstrations at the OFC last year. And this year, they have demonstrated the second generation, which has even better energy efficiency CPO modules. But Microsoft and Meta, don't think, the replacing the front panel pluggable optics with co-packaged optics in their switch part only, but also they rather expect more about the future of the computing, like applying, the CPO to the AI training, or even the future systems of disaggregated computing. And as a matter of fact, the market research company predicts that we're going to have a much larger market about this, application for the HPC or AI systems than the switch market segment. So CPO is expected to disseminate in the computing world, and then what is the impact of the improved CPO technology, and that will actually unleash the distance because it converts to the optical signal. And then naturally, or at the abstract level, it will suddenly, make the compute and the network converge together, right? Because you can't separate between compute and network, because the compute is expanded geographically by this CPO technology, right? And also, the co-packaged optics technology can be applied to coherent optical subassembly with the same, by applying the co-packaged optics, technology to the coherent optical subassembly, it might, it will commoditize the digital coherent technology, because that's the most costly part, but it's going to be, very mass-produced by the co-packaged optics. So it will further accelerate the, the distance expansion by the co-packaged optics, because they're going to suddenly get the coherent technology into the co-packaged optics as well. So once you get this, everything can be in optical domain just outside the chip. So the PCI Express or CXL, any sort of a protocol can be directly, transmit over a distance without any disturbances, and connect to the other computer node located in remote places. So you can realize optical row mode. Let's see why it's going. I want to come back. Okay. So all interconnects with any long reach, and that can be coexisting within the same fiber, right? Any of the network or interconnect at every layer can be coexist within the same fiber, for example. So this will, I think, create some sort of a new concept called Photonic Smart NIC. And this will be somewhat, the protocol programmable optical interconnects for all scale interconnects. And this can be, mixed together altogether as a huge system. So you can just, optically cut through and directly connect at the UCI Express layer or CXL layer or Ethernet layer, or you can convert it to a OTN layer such that this can even transmit over a wide area network. Okay, so the CPO technology will lead us to the convergence between the photonics and the computer and the network. So this enables a direct, end-to-end all optical connection between the remote places, and then exchange the data at any layer. So this will enable the system to enjoy the unique features of all optical, dynamic optical path network. And what are the unique features? They are simultaneous high bandwidth, low latency, low energy, and high security. It's the only optical communication, directly connected end to end. You can enjoy these, features at the same time. And in any of the packet, based networking, you can never get these, features at the same time. You can focus one of these, but you can never get those at the same time. The photonics can only offer. So here's the comparison between the conventional IP, packet-based network and, end-to-end optically switched all optical photonic network. And I often use the analogy, that IP network can be analogous to the automotive traffic, right? And so the energy consumption is, proportional to the number of vehicles or packets in this case. So the more vehicles or more data, you have to increase the energy consumption. And the latency, whenever you go to somewhere, by car, you cannot exactly predict at what time you are arriving to the destination. So same here, the packet. So the latency is not very well controlled, and even it's very stochastic, so it's hard to predict. And the data format and frame is dependent, of course, because you have to process on a computer basis. But an optical network, going through the optical switches and then directly connect end to end, of course, you need a very nice, sophisticated control plane, which is quite a challenge. But once you overcome this challenge, you can enjoy and enable the all photonic paths directly connect end to end, such that the energy consumption stays constant no matter how you increase the amount of data within the optical path. And also latency is going to be very low because the latency is only defined by the propagation delay of the lights, the wave propagating through the optical fiber. So it's very deterministic. And the data format and the frame is going to be, it doesn't care, optical switch doesn't even know what is passing through. It's in the optical switches. So it's analogous to more like a train system. So of course, this cannot be, this has to be there both, because of they are sort of complementing each other. So the question is how you can make use of these things at the same time at the optimum manner in terms of the energy consumption and pursuing the higher performances. So actually, it's a time flies. It's already back in October 2014, when we have succeeded in the first demonstration of a remote music session using ultra low latency 8K uncompressed 72 gigabit per second data transmission. And this was done in collaboration with a Japanese broadcasting company, NHK. It's a sort of a similar Japanese version of BBC. So we have a lab located in Tsukuba. It's about 60 kilometers away north from the Tokyo. And the western side in Setagaya, Tokyo, the lab of this NHK located. So we have connected with the optical path, switched by the optical switches in between. And so once you establish the path between these two remote places, you can exchange, the almost real time, the ultra high definition video each other. And this enabled, this is, you have an 8K screen and here's a real person. So they are actually, did the remote music session at the round trip latency of only 35 milliseconds. And this latency was almost determined only by the signal processing time of the the display and the camera. And because if you can calculate, fiber route was 170 kilometers, so the round trip time of the light wave was only 1.7 milliseconds, right? So well, actually, if you pick 2 points and then deploy the fiber and then do this, it's technologically, it's not that difficult, of course. But the real challenge is, we really need the very good fiber infrastructure, allowing, anyone, any place, any time to connect any of the, places anytime. So we really need to come up with the fiber infrastructure technology, which allows this sort of services disseminating everywhere. So here, right now, in the most of countries, the ROADM ring has been already deployed in its service. And now it's migrating towards the more like a mesh structure. And they claim that these days, C and L bands has already been filling up. So we needed to further extend the capacity of this given infrastructure. But in order to, offer sort of end-to-end path services, well, you need such system, right? And a control plane and everything. And you need more sophisticated optical, layer topology. And for 6G, you really need more fibers, because of this 6G requires a lot. And so in order to do that, we need a multi-cable, multi-layer sort of optical path network on top of, a very capable, packet switch network. And as I said, the optical switch doesn't consume much energy, almost negligible amount of energy as compared with high-end packet switches. So the more you exploit the optical fiber directly connecting end to end, the more you can save energy, right? So the more you deploy fiber, you can save energy. So I think this is a really important message, and so we need more fiber in order to make things green. So then the question is, if you have abundant fiber everywhere, and then the next issue is going to be how to control and manage, and then do we need a new architecture overall or something like that? But in order to do that, maybe optical layer has to be. Oops. Okay, so it has to be disaggregated and automated. So well, based on this kind of observations, our research center, Platform Photonics Research Center, was established back in 2020. And we are aiming at creating Photonics for Society 5.0. But as I have already explained, it's really important to things vertically integrated. So we do have research teams covering from the devices, packaging, and systems or software layer. And also we are operating a couple of consortia for building R&D ecosystem, because we are aiming at a huge, the target. And it's very essential to build the R&D ecosystem. One of which is the Silicon Photonics Consortium that offers R&D fab services with our in-house world-class Silicon Photonics processes based on 40 nanometer process line, and offering, running the 300 millimeter multi-project wafer. And then the other one is called Council on Devices and Systems for Next Generation Green Data Centers. That functions as a project management of NATO GI. It's a national project, the Next Generation Green Data Center Technology Development. And we are working together with a computing company as listed in here, and also photonics companies. And also we are offering the places for discussions, how we can, create a new value chain that can handle the photonics electronics convergence. Because, photonics industry and electronics industries were completely separated in the past. But now, the system requires us to converge. And then the question is, can we make such a value chain? Electronics packaging, for example, they never know how to handle optical fiber, right? And photonics transceiver, people, they never know how to handle digital, the chips. So we have to get together and understand each other and create a new value chain. And we definitely need such place to discuss in the very beginning. So from now on, I'd like to explain, some of our activities here in the context of this, the view graph I explained before. So first one is pushing this compute-com photonics trend by promoting the full photonics electronics convergence for the chiplet platform. And the second one is pushing further next generation beyond. So we believe that, at the end of the day, switch is going to be the bottleneck. That's going to be the bottleneck because it scales quadratically while the transceivers scales linearly, right? I mean, it's an array. So you really needed to, something to do with the switching, and then optical. So we have to think how we can promote the switching, optical switching. And the next one, maybe this is a little bit more scientific approach, but we might explore the leap by photonic computing, like neural or quantum, whatever. And the last one is more, architecture or software aspect. We are asking ourselves, what we can do toward the full automation of optical layer. So the first one, it's okay, I'm running out of time, and I don't think I can explain in detail, but I'm very happy to discuss with you if you're interested in any of these. But the first one is, the next generation co-packaged optics. So the thing is, the roadmap of co-packaged optics is yet to be discussed, and if you look at for further future. So up to now, many the startup companies or Intel or some the big players in the North America is sort of proposing or working on the chiplet, co-packaged optics technologies. And so we name it the 3.5 fifth generation, like a tiled co-packaged optics. It's a socket based, so you can attach or detach the optical transceiver module looks like a tile and like this. And then the next stage is going to be fully, in package integration of photonics and electronics, like IR Labs doing. And then the next one is, so we'll be, maybe this is actually what we've been working for a decade, and we are forming a polymer-based waveguide on top of a printed circuit board, such that the optical chip and electronic chip can be co-packaged on the same substrate as shown here. And then this will, lead us to more functional, the board completely under the electronics photonics convergence. So in the end, we may be able to put some more, optical functional, components like optical switches inside the among the chiplet board, and to make the system more efficient or usable. So this is a quick view of what we have been working. So here's a polymer waveguide on top of a printed circuit board, and then on the printed circuit board we embed the silicon photonic chips underneath the switch ASIC. And this switch ASIC actually, to now, it's not a real one. It's just a mock-up sample, but we did sort of a proof of concept demonstration. So the important aspect, so far we are working on more focusing on the optical side. So what we do is we embedded silicon photonics inside a printed circuit board. And then, the silicon photonics this optical signal comes out from the edge. And then, we need some technology that couples the output from the silicon photonics to the polymer waveguide on top of the printed circuit board. And then we are trying to, form a 3D polymer micromirrors. And then we have coupled so far and then transmit 100G PAM4 transmission. and we measured the temperature dependence of the performance, and so far we have succeeded say stable operation up to 85 centigrades. So the second one is optical switches in composable disaggregated infrastructure. This is simple, just a conceptual proposition, but it's not a really complicated thing. It's very simple. If you replace the electrical switches, meant for the composition or reconfiguration of the disaggregated computing with optical switches, and still you need a packet switching, of course, for the computation purposes. That will do done by the electrical switches, but in that case you can have a much smaller scale electrical switches because it's the purpose are different. But if you try to realize both the reconfiguration switch and the packet switch with the same common switch platform, you really need a huge size of electrical switch. So if you discriminate the roles in that way, and one optical switch and one electrical switch, and then in so doing, this is very simple story such that this should be very quite right, and then you can save a lot of energy in the switching part, because the optical switch doesn't consume almost nothing as compared with the electrical switches. So we are working on the optical switches based on silicon photonics. There are many approaches, very different mechanism platforms. And recently, maybe you have been aware that the Google data center have been utilizing the optical switches based on MEMS for over 5 years, and they have deployed thousands of switches already, which just announced last year, and we were very surprised. But anyway, we have been working on the silicon photonic switch, where it's different from the MEMS switch. It allows a much faster switching speed up to microsecond. So yes, we've been working for more than a decade on the silicon photonic switches, and up to now, we have fabricated a polarization diversity based 32 by 32 silicon photonic switches. So it carries more than 1,000 Mahasindra on a single chip monolithically, and operated very in a stable manner. So just to demonstrate, we're utilizing this switch and then making sort of a recirculating configuration, and we emulated the fully loaded operation of this 32 by 32 switch, and the optical signals going around by 99 times. So this single switch, and we succeeded in the the data transmission. So which means that this switch is capable of forming a 9-stage Crow network fabric. Then with given the 32 by 32, so if we have numbers of these kind of switches and forming in the 9-stage Crow network, and then we can offer the very high radix, as high as more than 130,000 radix, and well, this just demonstrated the potential of our silicon photonic network. And another one, quick look at, we don't extensively work on these topics, but because we have a very nice, a large scale silicon photonic integrated circuit platform, we came up with our original, photonic support vector machine type, and actually demonstrated very high recognition accuracy. And also we have applied exactly the same silicon photonic switch platform for doing some quantum walk experiment and exhibiting very stable operation over long hours. And that's all. I'd like to quickly explain the how we can connect the physical layer with the software layers. And up to now, if you are familiar with a consortium called Open RODAM or Open Config or TAP Open Line System, they are trying to virtualize the optical layer. But their model, handled by the software layer is still yet somewhat abstract from the real hardware it is. So we found, that there is a gap between the real hardware situation and what is defined as a physical layer in the software defined networking consortium. So we were thinking about how we can fill this gap. So we really need a hardware abstraction layer for mapping between the real hardware composition and the RODAM-based model. So I think we are running out of time, but so if we have a component-based model, describing any of the optical component function can be described in a mathematical manner, and then automatically compile those information to create the model of the more abstract, whatever it is. And we came up with what we call the functional block-based disaggregation model, in short, FBD model, where we are using integer linear planning formulation to describe any of the optical components like WSS or cross connects or even a splitter or even amplifiers and isolators. And so in so doing and putting, the connection together with the connection information among these functional blocks, you can automatically compile those things because it's written by the ILP formulation. You can generate automatically the topology of the real optical layer. So this is nothing but this, the ontology of the optical layer. Whatever it is, you can put the blocks and then they are described by the ILP formulation. And then, together with the connection information and then, that input to the CAD program, and then they can automatically produce a net list from which we can do some sort of path computation program or whatever. Or also you can utilize that for inventory monitoring those things. Okay, so, I'm going to quickly go with this slide. So you can have a blade, within some sort of optical function inside, like WSS or amplifier or whatever. But if you plug in this to a rack and then just like a USB device, you can construct a mechanism such that, this device contains some sort of information about what it is, and then it can be, automatically recognized by the rack controller, and then everything can be updated automatically. So this is all about the disaggregated optical layer, stuff like this. And just quick demonstration. So by making use of this, platform, we have demonstrated the automatic sort of maintenance of the optical nodes. So here we first start, the setting up the path, and then this path is transmitting the 4K real-time uncompressed data from a remote place. In this case, it's from Tokyo to Tsukuba. So you see sort of Tokyo scenery from here, and then we're gonna emulate the fiber cut. And so this fiber cut is automatically detected, of course, right? And then the orchestrator is considering, how we can restore the path and then restore this, the video transmission. And then it finds that, current topology doesn't allow, you cannot find any optical path restored because of the limitation of the topology. So they decided to add some new components in certain node here. And in a scenario is automatic recognition like a USB device by the controller, and then of course the fiber has to be connected manually, and then the connection information can be recognized automatically, but anyway, you have to input to the system. And then, so you do this, the compilation again, and to get the, updated optical layer. And then you can do the computation, path computation, and then find the route for restoring detouring the fiber cut path, and then the orchestration will recover this path and so forth. And this took only 5 minutes, but now if you ask NTT or KDDI or whatever, it may take days, right? I mean, so this is something that it's nice to have. Okay, sorry, I'm almost running out of time, so I think I'm going to wrap up. So I think I have explained the FED model bridges optical layer to the cloud, such that everything is on the same platform from the compute to the network, right? So you have a disaggregated compute nodes resources, and it's disaggregated optical functions, and then you have city, town right here, and then you can think of which resource you want to deploy, and then how you want to connect, and how much bandwidth you want to offer. And in so doing, you can realize any of the network with the requested latency or whatever diverse applications, and then you can do the holistic optimization of all entire digital infrastructure. Okay, so I think this is my takeaway message. It's a great time for next round of the journey, because we came up to the space now, right? And then we're still at the 1D point-to-point layers, and then we have to extend it to 2D mesh-like, and 3D, and the convergence from the coverage from underwater to the space. And then we needed to redo all over again and extend the bandwidth and everything. So I think I'm going to skip, we are working also some sort of a space things with the silicon photonics, by bending the 100 by 90 degrees such that the optical output can come vertically from the surface of the wafer. And we can utilize it by combining with optical switch, like a core-to-core switching module, and also some sort of a beam steering devices. So I think I have convinced you enough that building an ecosystem is very important, because this is not something you can do by yourself, right? I mean, we really need the joint collaboration widely as possible. Or otherwise, we can't do any of the, the sort of holistic optimization. So it involves a whole range of the technology and application area. Okay, so as conclusion, so R&D for photonics electronics convergence for future involves too many technology areas and the layers for only a few research entities or even a nation to cover. So, global cooperation for building an ecosystem is, I think, very essential. Yeah, that's all I have today. Well, thank you very much, and good luck on your project. Thank you very much.
Thank you, Dr. Shu Namiki. A lot of very interesting thoughts, sort of peek into the future, energy efficiency, cyber physical systems, software-defined optical communications, and so on. I know there are a lot of questions from people here, but I would suggest that we defer the questions to the coffee break. Dr. Namiki is going to be here for the rest of the day as well, so you could interact with them at leisure. So with that, let me thank Dr. Namiki once again for his excellent plenary. And as a token of appreciation from the organizers, I have this to give you. Yes.
Thank you, sir. May I now request Dr. David Koipale to join us on the stage for presenting the memento to the session chair. Thank you, sir. Before we proceed to the next session, let's take a short tea break. We have made arrangements just outside this hall. As we are running short of time, be back promptly by 10:30 as we have some more exciting sessions coming up. Thank you.
Hello, are we audible to you?
You're also there in this, right?
Yeah.
If you speak in mic only, he will audible.
Hi, are we audible?
Yeah, I can hear you.
Yeah, thank you.
Okay. You want to see if the slides show up?
What is the issue now?
Sometimes it was lagging.
I think
it's all muted, right?
Okay. Radha, can you hear me?
Yeah, I can hear you now. You guys were on mute.
Yeah, sorry. Hi, how are you?
Good, how are you?
Good. Yeah, I think we're trying to stay on schedule. We
Sure.
should be getting people back into the auditorium in a few
Do
minutes.
you want to see if I can share my slides?
Yeah, just a second, because they're trying to get a cable to project you onto the main screens on the stage. So
Fair enough.
After his talk, this is the next.
but we need to check with the slide share that is also working. So Shalab has his own laptop. No, I'll just speak here.
என்னோட லேப்டாப்ல ஒரு HDMI கனெக்ட் ஆகும் அதுல வந்துருச்சு நீ எடுத்துட்டு வந்துட்டாங்க
Sound set? It's not stable then. Okay, வாங்கிக்கோ இப்படி வாங்கிக்கோ. Start பண்றோம். You should call people to come inside.
Yeah.
போடியம் மாத்தி விடுங்கண்ணா மாத்தி இதுல தானே இருக்கு
இது வைக்கணுமா அது வைக்கணும்
இது வைங்க இது வைங்க ஸ்டார்ட் பண்ணிடுவோம் நான் வச்சிருக்கேன்
Yeah, better you give. Otherwise, if they turn their head, it is not audible.
Okay.
Better you give it. I ask them to use this.
Yeah, make an announcement now. Start.
Cable is good. Bad.
No, it's not proper also. Something happened. No, other people want.
லேப்டாப் நமக்கு அதிகமான அதுதான் actually this session we can connect from there as well.
Yeah.
That you can
They have put, but not to say time we didn't know. Now it's okay.
Straight away, we will move on to our first session titled as Transceiver Technology, Current and Future Trends. Please give a warm welcome to the session chair, Mr. Bhiman Chattopadhyay, the co-founder of Confluence.
Hi, good morning, everyone. Let me extend my warm welcome to the workshop on advances in optical communication. This session, the first session in the morning, is on transceiver technology, current and future trends. So we have three speakers for this session, and we would start with Dr. Radha Nagarajan. Dr. Radha Nagarajan is the Senior Vice President and Chief Technology Officer of Marvell's Optical and Cloud Connectivity Group. In this role, he manages the development of the company's optical platform technology and products. Radha joined Marvell from Inphi, where he served as the Senior Vice President and Chief Technology Officer of Platforms. Prior to joining Inphi, he was a fellow at Infinera, where he was focused on the design, development, and commercialization of large-scale photonic integrated circuits. Radha has been awarded more than 230 US patents and is a fellow of the IEEE OSA IET UK. In 2006, he was awarded the IEEE LEOS Aaron Kressel Award in recognition of breakthrough work in the development and manufacturing of large-scale photonic integrated circuits. Radha holds a B Engineering from the National University of Singapore, Master's Engineering from the University of Tokyo, and PhD from the University of California, Santa Barbara, and in electrical engineering. So over to you, Radha. So we have 25 minutes for this first talk.
Okay, thank you very much for the introduction. Let's see how well this works.
Radha, we cannot hear you. Can
Okay.
you unmute yourself?
Oh, am I muted? I'm unmuted here. Can you hear me now?
Radha, give us
I am actually unmuted.
Okay. Yeah.
Okay. I'm ready to go. Do you see my slides in the slideshow mode? Okay, looks good. First, no, you're looking at the wrong screen. Let me go back and stop share. And let me share. That's interesting. All right. Okay, is it in the slideshow mode? I will go with this. We'll go with this, and then we will correct things as we go. First, thank you for the invitation to this workshop. Wishing you all the best in the path you're on. Today, I'll present Marvell's view on advances in optical transceivers. As the session chair so kindly introduced, we are in the optical transceiver space, but it's very specific which transceiver space we are in, and I'll get to that in a moment. Okay, good. So a little bit of a background on data center interconnects. This is actually a collection of data centers. Collection of data centers, mostly in the United States. Oregon, North Carolina, Iowa, New Mexico, and you have a couple in Sweden and Ireland as well. The first things they notice, data centers are huge. Perhaps not quite in India yet, but all over the world, the scale is large. Even with these scales, it is quite difficult to get everything done in a single contiguous building. So you have interconnects within the building and interconnects between buildings. And I am going to look at these one at a time, so we have a better perspective on where some of these things are headed. All right. First, a brief introduction. Will be a couple of slides giving you the background on optical connection data centers. Let me see if I can get the pointer on. Maybe just easier. So right at the bottom, where you have the servers, and then the servers connect to the top of the rack switch. And then you have the layer 1 switching, layer 2 switching. And that usually defines a modern day data center. And then you have the connection to the campus or region and zone. And then you have the DWDM networks that connect between data centers, connect between the regions. These connections here tend to be DWDM connections as well. So the scale is between racks or within a rack, they tend to be under 100 meters. And within a data center, they tend to be 2 kilometers. Campus networks of the order of about 80 kilometers. And if you go to an extended campus, and if you go to a region where you have a number of data centers that are connected, they get to about 120 to 80 kilometers. The distances matter because the choice of technology that you use for data centers depends largely on the distance. So there are 2 primary modulation technologies. First is PAM4 or NRZ evolved into PAM4. IMDD's intensity modulation and direct detect versus coherent. So what determines what? Distance. Today, we are 800 gig transceivers. I'll work your way up to 800 gig pluggable transceivers in a moment. And if you were to look at long haul metro, the distances are given just below there, or DCI, data center interconnection aggregation, a lot of it is coherent. The further you go, more coherent networks you see. Once you get to campus under 10 kilometers, when we say 800 gig, it actually means 8 by 100 gig optical. Closer and closer to the data center, inside the data center, rack to rack, they tend to be intensity modulation and direct detect. When you go to 1.6T modules, which is 8 times 200 gig, which is inside data center, and outside data center, it could be a single wavelength or 2 wavelengths of 800 gig, you find that something interesting is happening. The coherent is moving very close to the data center, and at some point, you might find coherent inside the data center. And that is the trend. At 3.2T, we think the intensity modulation, if it happens, we are looking at PAM6, will probably happen just within the building. There are lots and lots of discussion how we would get to a 3.2T pluggable module. But that aside, these are the challenges that we face today. Okay. And the specialty at Marvell is what's called the between a campus and a DCI aggregation network, anything between 80 to 400 kilometers. That's where the pluggable coherent modules play. The first generation 100 gig modules were PAM4, but they've progressively become coherent. So keep that pink area in mind while I give you some background as to the interconnects within a data center. All right. So if you're wondering what pluggable modules look like, what transceivers look like, this is what they look like. Every flavor. These are modules that plug directly into the front face of a switch or a router and converts that into an optical transport system. You have all the way from 40 gig in this chart up to 100 gig, varieties and varieties. This is just from one vendor. There are probably a dozen vendors out there who actually make these things, but these are for inside data center applications. So intensity modulation, coherent modulation formats, but essentially, what materials do we use for optical modulators? Traditionally, have been indium phosphide for DMLs or EMLs. This is electro-absorption modulated lasers, or electro-absorption modulators. They have our single mode communications tend to be indium phosphide up to now. And gallium arsenide is usually VCSELs for multi-mode and for short reach applications. Progressively, things are moving to silicon photonics, and that's what I would talk about. We've been primarily working on silicon photonics, and I saw the plenary speaker allude to silicon photonics, and there'll be 2 other speakers after me, and I have a feeling they would be touching on silicon photonics quite a bit as well. Traditionally, long haul has been lithium niobate, the linear electro-optic effect to modulate the laser switching voltage in a Mach-Zehnder modulation format. I just noticed that my slides disappeared. Is that a problem on the other side? Should I wait?
We can see your slides.
All right, good. I can see it now too. Very good. I wanted to give a very brief introduction to silicon photonics foundries. These tend to be the commercial foundries that I want to talk about. Tower Jazz or Tower Semiconductors is a popular foundry for silicon photonics. Global Foundries. Tower is on the West Coast, Global is on the East Coast, Silterra is in Malaysia actually, and Intel has its own internal foundry, and AMF, Advanced Micro Foundry, is in Singapore. So for those of you who do not see silicon photonics on a regular basis, I just call it a work of art, whether it's a bend or a waveguide or a coupler or a directional coupler. I'm not going to go into any of the details of these devices. I'm hoping some of my subsequent speakers would. But you build these devices on silicon. They look very different from the silicon circuits you're used to. None of them are really Manhattan geometries. These are optical waveguides, optical modulators. And the detectors tend to be primarily germanium, although there are approaches where you could potentially integrate a indium gallium arsenide detector directly onto silicon. But the native detectors tend to be silicon, whether they are regular PIN diode or MSM or an APD. This is metal semiconductor metal, or an APD avalanche photodiode. There are a variety of them. The most common one are the germanium PIN photodetector or waveguide germanium photodetector. Okay. What does the market look like? The market's actually quite big. What sort of pluggable modules get deployed in data centers? It goes all the way from 1.6, 1 gigabit per second, which is actually, I thought it would have been dead by now. Apparently, we're still deploying some 1 gigabit per second pluggable modules. At Marvell, we focus on everything above 100 gigabits per second. That is the backbone of data centers today. Although there are 50 gigabit per second modules, 50G modules in deployment, essentially all of data center deployments tends to be 100 gigahertz, 100G and above. If you were to look at the breakout, this is number of modules. Some of these modules are not very expensive. So if you wanted to look in terms of data center revenues, they tend to run between $6 and $8 billion a year annual sales. So if you were to look at even by 2021, 22, the 100 gig sales were already going down. 200 gig modules kicked in. Today, the mainstay of data center deployments are 400 gig with 800 gig modules kicking in very strongly. And this year at OFC, that's March, not too many months ago, many vendors were demonstrating 1.6 terabit modules based on DSP and TIA and drivers that Marvell supplied. We have a fairly large market share of most of these DSPs. We are first to market, and we are first to market in deploying 1.6T pluggable modules as well. I'll get to that in a moment. The interesting thing is, this does not include the latest AI craze. These are not involving, including AI-centric deployments. All of these is what I would call a front-end data center network. And because of AI, the front-end data center network is also growing between 18 to 20% attach rate, but the AI-centric deployments are a whole universe unto themselves. And as you're well aware, optical modules, and a lot of them are 800 gig, and they are just kicking into high gear for AI-centric deployments. It's yet to come. Next year would be in full swing. Okay. All right. I would describe in some detail 100 gig silicon photonics modules that we built for between data center interconnects. We are still shipping these, by the way. And then I'll go on to 400. This was 100 ZR, and it's a PAM4 module. A typical pluggable module in this type of environment has a DSP ASIC A pluggable module, it's just a lot of power supplies and a controller and other miscellaneous ASICs, by the way. And then you have a transimpedance amplifier on the receive path, a driver amplifier on the transmit path, a laser. And we built a 2 lambda. This was a 2 lambda 100 gig chip with integrated Mach-Zehnder modulators and photodetectors. This is the first generation, by the way. So the output is 2 by 28 gigabaud. So it's about 56 gigabit per second. The data rate was actually 50 gigabits per second. And this is essentially an FEC overhead. If we have some time towards the end, I'll explain the FEC to you. It's a standard CoE4 interface, and it's a standard QSFP28 MSA, multi-source agreement. This is a standard module that gets deployed in data centers. And the input was 4 by 25 gig. This is KP4 encoded, so it's 25.78125 NRZ, and we convert it into a PAM stream. As I said, this was the first generation. A lot of it is published in 2018. The Mach-Zehnder modulators for the first generation had about 25 to 30 gigahertz bandwidth. The current generation modulators have well over 60 gigahertz modulation bandwidth. This is what a PAM4 signal look like. If it's NRZ, it's a 2-level signal. PAM4 is a 4-level signal. So it encodes 00, 01, 10, 11 as a signal. And the PDs had a bandwidth of about 15 to 20 gigahertz, and dark currents run under about a microamp in the region where we use, all the way up to EDC. This was a PAM4 modulation format, so it needs dispersion compensation. Once you go to Coherent, you don't. But we actually deployed this in multiple different fibers. The favorite fiber was an all-wave fiber, which is equivalent to an SMF28. This is in full deployment. This is one of those things I can tell you who the end customer is, Microsoft in this case. And Azure Network has a lot of these 100 gig modules in deployment. Microsoft went out and actually told the world where they procured their modules from. So I'm not bound by NDA on this one. So you take these switches, and then you go to a line system, and you go to a fiber spool. You go to the other end, and then you make a comeback. There was actually a campus-wide network that we considered, which didn't go into full commercial deployment. This was a 4 terabit per second interconnect. Once you fill a fiber, this is what it looks like. It's totally amazing. This was these pluggable modules could accommodate 36 pluggable modules. So 3.6 terabits on single fiber. And a fully loaded system will work up to about 4 terabits per second. And these are distances of well over 10 kilometers, between 10 and 80. The typical deployment scenario is below 80 kilometers. Okay. And this is the first generation DCI between data center modules that we produced. The ones that we are shipping in volume right now is the 400 gig modules. We've moved on, it's no longer PAM4. It's a coherent pluggable module in a very small form factor. It's 400 ZR and 16 QAM, which is a coherent modulation format. To do this, we built a silicon photonics chip again, but it's somewhat of a more complicated silicon photonics chip. It's got a nested Mach-Zehnder modulator, and it's got a T and TM hybrid. It's got polarization beam splitter rotator. It's got a polarization beam rotator combiner. And then we have a power splitter for a tunable laser. So there's a lot going on a single silicon photonics chip. This is a receiver block, the transmit block. The receiver PDs over here, which are germanium PDs. And this is a power split between the local oscillator in the receiver and the transmitter. And for these, you needed quite a bit more bandwidth. These are 60 gigabaud signals. So the modulators had about 40 gigahertz bandwidth. We had to build polarization independent components. We had to build things which were polarization independent right across the C-band, because these are DWDM networks. And photodetectors are not as difficult to build. They tend to have 50 to 60 gigahertz bandwidth. When they get to about 100 gigahertz, you lose some responsivity. But until then, they're not too difficult to build. And the modules are pluggable modules again. And inside a module, you have a coherent DSP, transimpedance amplifiers on the receive side, a driver amplifier, a tunable laser diode. This was a single wavelength pluggable module. There were 8 25 gig inputs, PAM4. We converted that into a single 60 gigabaud, 16 QAM 1 lambda, nominally 80 to 120 kilometers. This is the state of the art in deployment for a pluggable module between data centers today, and its shipping in volume. Okay. And you can take this, now it's coherent. You can load the system even more. And this particular, we had 64 wavelengths at 400 gig. And if you do the math, it's 25.6 terabits per second per fiber. It is a huge number, 25.6 terabits per second per fiber. That is the nominal capacity of a single mode fiber. There are people who've done a lot to improve the capacity, but in deployment, when you need OSNR margin, when you need performance margin, it's not so easy to squeeze in a whole lot more. This particular demonstration was 6 bands. The EDFA is a noise figure of 5.5 dB. Launch power was 2 dB per lambda, and we had a lot of OSNR margin. And this demonstration was a couple of years back, maybe 2 years ago or something, just as we were starting to ship QSFP-DD modules into this market. All right. How do we get to higher and higher data rates? It never stops. It's a perspective on our side. And this is some math going back to undergraduate days or graduate schools. In a system dominated by additive white Gaussian noise, that's a luxury, by the way. Reality is neither white nor just simply additive. If you were to look at this, this is just Shannon limit. But a better way to write the Shannon limit is to write SNR and as a function of C over B, which is actually spectral density. How much data can I squeeze per unit bandwidth? That's what I care about. That's what deployments care about, right? If you were to look at something like this, then you would notice that the SNR is constant with increasing baud rate. I mean, who cares? If you want a larger baud rate, you just go to larger bandwidth, and SNR is supposed to be constant, but it never is, right? But within certain constraints, SNR does not scale with bandwidth if the bandwidth is going up at the same time. What happens is if you wanted to squeeze in more data for the same unit bandwidth, then the SNR grows exponentially. And things get dicey when things grow exponentially. All right, let's take an example. 400 gig, that's what's shipping in volume today. This is PAM4.
We have around 5 minutes.
There's a huge echo in the background. I hope I'm not running late. So if you were to look at 16 QAM, which is 2 PAM4s in an I and Q axis, if I want to scale this, inside data center, PAM4, we can get to 8 lambdas, right? You just double the number of lambdas, right? It's outside data center, it's the same. Lambda scaling. It's not that easily scalable. You have problems with power, size, and cost. The other way to do it is just increase the baud rate. What is wrong? Let's go to 200 gig per lambda, right? That means at 100 gigabaud data rates. Or if you wanted to double your data rate from PAM4, you really have to get to PAM16. And for 16 QAM, you need to get a 256 QAM. This is impossible. We would run out of SNR way before this. So realistic solutions would be something like 64 QAM, perhaps for long haul transmission and PAM6. But at 800 gig today, we thought we have to go here. We've stopped. We've gone directly to 200 gig per lambda. We could build it. We have. And at PAM4, 200 gig per lambda, the solution we picked is 113 gigabaud PAM4 signal. Okay, scaling. Speed scaling never stops. This is some of the best photo detectors we've built. It's well over 75 gigahertz bandwidth. Mach-Zehnder modulators, they're well over 60 gigahertz bandwidth. And they're headed. These are silicon modulators right now. We haven't done anything else to it. They're headed to past 60. We have demonstrated things between 60 and 80 gigahertz bandwidth. You know, everything is analog. I need amplifiers. We build amplifiers for this application. The transimpedance amplifiers have over 80 gigahertz bandwidth, and the driver amplifiers have over 90 gigahertz bandwidth. So both of these are suitable for very high baud rate transmitters and receivers. Okay. This is what we demonstrated this year at OFC in March. 224 gigabit per second PAM4 at 113 gigabaud baud rate. To make something like this, you need extensive compensation techniques, strong equalization blocks like MLSD, low latency, low power FEC, in-band telemetry. The list goes on. It's a tour de force, and we are finally at 200 gig per lambda, and this is state of the art. If you take 4 of these, you can make an 800 gig modules. And what they did at OFC this year is they took 8 of it and made it 1.6 terabit per second pluggable module for inside data center applications. Outside is still 400 gig per lambda, going to 800 gig per lambda. That's a state of the art. All right, FECs, I don't have a whole lot of time. I'm running out of it. So FECs are an interesting thing. Net coding gain improves as your overhead gets higher and higher and higher. Anything past 5 to 15%, 5 to 15%. You know, you're not doing a whole lot of favor for yourself.
2 minutes to close.
Okay, I will finish it. And you are on the KP-FAC and SFAC regime. All right. Integration. I want to touch on these briefly. As your data rates go up, you have to actually start integrating these directly on silicon. This is a silicon photonics wafer on chip, by the way, on which we have TIAs and drivers and capacitors and all kinds of things integrated. What we do is we bump the electronics and then we do a flip chip on it. This is our first generation platform. Our second generation platform is a whole lot more complicated. We do these things at the wafer level, and the silicon photonics is the interposer. And you get one of these dies and you put them on a substrate, and then you have a DSP at the back, and you actually have a very, very compact transmitter modules. All right, and you can build co-packaged optics with this. And this is what we demonstrated with our TerraLink 7 switch. And this is a live demo this year. So you can actually put the optical modules not in front face pluggable. You can put them directly on a card right next to a switch. That is where the world is sort of headed. Thank you. I hope I made it on time.
Yeah, Dr. Rather wonderful talk, starting from the basics and taking it to the height of what you're doing right now. So in the interest of time, we would take the question at the end. We would invite the next speaker to come over. But before that, I want to thank you, Dr. Rather, for this wonderful talk and as a token of appreciation, we have a memento for you, but because we cannot hand it over here, we would send it across to you, and you should be reaching. It should reach you in a week's time. So thank you again.
Which will be perfect. You can mail it to me. I will try to stay on for a little longer. It's getting to be about 11 p.m. over here. I may not be around to take the calls, take the questions, but wishing you all the best in your workshop. Good luck.
Okay. Thank you.
All right, let me see if I can stop sharing. There we go.
Let me now call down Dr. Sudarshanan Srinivasan for the next talk. Dr. Srinivasan received the Bachelor's in Engineering Physics from the Indian Institute of Technology, Madras, India. He received his Master's and PhD degree from the University of California, Santa Barbara, California, USA. After a brief stint at Juniper Networks and Hewlett-Packard Enterprise, he joined the Electrical Engineering Department of IIT Madras in January 2022 as an assistant professor. His research interests include integrated diode lasers, modulators, and photodetectors, heterogeneous material integration, and nanofabrication technology. He has authored and co-authored over 35 journal papers and 2 book chapters. Over to you, Dr. Sudarshanan.
Hello, can you all hear me? Okay, thank you, Biman, for the introduction, and thanks to 2 speakers that came before me. They have probably laid the stage very well, and in honesty, you'll probably see a lot of similar messages being sent even in this talk. So as I saw Professor Namiki's talk and then Radha's talk, the thing that I kind of remembered was this little story. I'll probably start with this. It's probably a bit interesting. I think some of you may know this, but there is a very famous dip in the measurement of speed of light somewhere between the 1940 to 1950, right? These are metrologists all over the world who are trying to measure the speed of light to very, very good accuracy. And most people during that time actually believed that the speed of light had dropped, right? So, but then more careful measurements have been made, and we now have a much better handle on that. But when asked this question to a head of a metrology department, he called it intellectual phase locking, right? So sometimes this tends to happen in the community. But I kind of want to mention this because I don't want you guys to see the same message and see that there might be some intellectual phase locking happening, right? All of them are sort of wrapped in their world about what they believe needs to happen. So this, a lot of what we say and what I'm going to be showing goes to say that these problems are real, right? So there's more than one source. So just a brief word about silicon photonics. I know this is an optical communications workshop, but integrated photonics goes well beyond optical communications. That went pretty quickly. But yeah, I just wanted to say that we believe integrated photonics has a much broader impact to the human community, right? So as the societies get more complex and sophisticated, the list of what we consider basic human needs is growing, right? And the newcomer in this is data, right? And just to quote a recent Nobel laureate, Donna Strickland, most of you know her, she said photonics is going to be the technology of the 21st century, right? So we'll see why she means, what she means by that, at least in this context, in this forum. So this is a very basic diagram. Hopefully this is something that most of you have learned in your undergraduate. So most, sorry? Yeah. So any system basically takes in some energy input, and there's a certain efficiency of the process, and then you have work and waste, right? And some facts of life, we waste more energy than we consume. So the size of the arrow actually indicates that a lot more of it, the energy that we consume to do any process that we want to do, is actually wasted in heat, right? So how can we actually reduce energy usage? One is to reduce work, but that's probably not happening, at least with the data trends that we have been shown from the previous two speakers. The only thing that we are left out as engineers is to improve efficiency, right? And this is what engineers do, right? While these graphs might look pretty mundane, I think it's very, very impressive. So if you look to the graph to the left, right, while the workloads have actually tripled and the internet traffic over a period of 6 years has more than become 5x, you can see the data center energy usage has remained flat, right? I just want that to sink in. So that's a very remarkable feat. That almost means that there's been an exponential improvement in the efficiency in which we've been handling data. And how is this possible? So the nice thing about the digital economy and the digital technology is the more and more compute power I make, I can actually feed that back in a positive feedback cycle to actually make better computing systems, right? So this is essentially the bedrock of why we make technology transitions in periodic stages, right? We could not make the 22 nanometer technology 50 years ago because we needed the 40 nanometer technology to tell us how to make the 22 nanometer technology. So similarly here, we actually have our own systems, interpreting how well our systems are working, and then turning the powers of these modules to a low power state when they are not being utilized, right? So these kind of gains that we've seen in the last 6 years has just come from monitoring and improving our utilization efficiency. So this is a chart that is exactly picked off again from Professor Namiki's talk. But this is what I meant by it not being an intellectual phase locking, right? This is a serious problem. And we engineers certainly believe that if you want higher data capacity, and if you want more processing information, the amount of energy you're going to consume is going to increase, right? There's no magic button that just reduces this. And these data centers are actually en route to consuming and are having a carbon footprint that's greater than most countries. So what exactly are these data centers doing, right? So we saw some of the pictures from Radha on the size and scale of the data centers, but most of the power that goes into these data centers is just to keep these servers in a cool room, right? Just like the ACs that are keeping us cool here, the data center just spends more than half its energy in just converting power from the electrical lines that's fed to it and just keeping the servers cool. So even though the plumes that you see there are not carbon dioxide plumes, it's just water vapor. It's just the heat cycle of water that we are spending half our energy on. And what is it we are cooling? I guess there are three. The one that I'm here to talk about is the networking aspect. So remember that when we make efficiency improvements at this scale, the scale at which we will save energy is much, much greater than 1:1, right? Because we'll require less cooling when we use less power, because we waste a lot lesser in terms of heat. So I think this conversation has been quite convincingly been transferred to many of the data center operators today. So there's no longer a doubt that copper is losing the battle with optics in terms of data transport and power efficiency. And we are moving more and more towards on-rack and within board and chip-to-chip communications with optics, right? So here is a slide just to give you a sense of why 1 watt matters, right? Even a savings of 1 watt per transceiver can have fairly significant impact on your entire network infrastructure. So if you just consider a 10 data center network, you probably roughly require about 10,000 transceivers to connect them. This is just the interconnections that go between them, not the interconnects within the data centers. And 1 watts of savings actually translates to almost about 2 crore phones, smartphones being fully charged, right? So just to give you some perspective, just 1 watt of savings over a year. So I'll probably not labor these points. So I think the previous speakers have mentioned that the industry has fairly aggressively moved and quickly moved from NRZ to PAM4. And we have every flavor transceivers populating a bunch of these server racks all over the data centers. But I just wanted to give a glimpse of what exactly goes into some of the more conventional transceivers 10 years ago, some of the gold boxes that you see. But as Radha showed before with silicon photonics, the way we do optics has completely changed, right? So no longer are we seeing gold box packages. We don't see hand-assembled prisms like you see at the bottom left. Very intricate work, right? So we no longer have that. If not for the yellow tinge on the chip to the right, you wouldn't actually be able to tell the difference between a photonic chip and an electronic chip. So this is where the world is headed, and this is where IIT Madras would also like to contribute. So what makes photonics special, and why has it taken us so long to be able to do this, right?
Around three minutes.
Yeah, I'm almost done. I just have my vision. So here are some of the key points that we would like to work on, and I think the industry is fairly aware of, which is just like Professor Namiki mentioned in his plenary talk, the people who have been doing electronics don't know how to handle optics, right? And part of the reason is the interfaces need to be clean. And by this, it's just not the know-how, but it's also the ecosystem around it, which is equipment vendors who can help us take care of chips or handling these chips. Fiber packaging and fiber alignment is very important. Correction of temperature is fairly power hungry today. And wafer level testing for photonics. This is a very key important point in terms of bringing down the cost. And finally, laser integration. So here is the vision at IIT Madras that quite a lot of us within the photonics group would like to champion. This is just a sliver of the vision. There's a much grander vision going on, which is really, we would like to set up an R&D program for co-packaged optics, right? We know that's where the world is headed. And here are some identified key strategic research areas and some of our objectives for this vision. And we believe it will have a fairly significant impact in the country's R&D programs. And we believe this workshop is a forum where I'd like to thank a lot of the people who've made this happen and hopefully will continue to support us going down in the future. Thank you.
Thank you, Dr. Sudarshanan, for this very impactful talk. Like, it started with a glimpse of like why we are doing what we are doing. That was very, I think that's something that will stick to our mind. And also you talked about like the overall vision of where we are heading towards. So thank you for that talk. Okay. Yeah, as a token of appreciation, we'd like to give you a memento for you. The next talk in this session is by Dr. Shalav Gupta. Dr. Shalav Gupta received BTech degree from the Indian Institute of Technology, Kanpur in 2001 and MS and PhD degrees from UCLA in 2004 and 2009 respectively, all in electrical engineering. For his PhD, he worked on the development of high-resolution, high-speed analog to digital converters using optical techniques. From 2003 to 2006, he worked in the industry on the design of analog integrated circuits for high-speed serial links and RFICs for wireless communication. He also spent some time at NEC Labs to learn and contribute in the area of high-power speed coherent optical network at Princeton, New Jersey. Since 2009, he has been with the Indian Institute of Technology, Bombay, where he is currently a professor of electrical engineering. His current research interests include electronic and photonic integrated circuits and systems for wired, wireless, and optical communications, and more specifically, high-speed interconnects. He has recently also founded a commercial startup called Aortic Labs to develop optical transceivers for next-generation energy-efficient data center interconnects using techniques developed in his group at IIT Bombay. Over to you, Dr. Shalav.
Thank you for the, am I audible? Thank you for the introduction and thanks for inviting me to this session. It's great to be here. Already the previous speakers have set the stage. They've already talked about many of the things which I wanted to talk about. So it'll help me in speeding up. Again, this slide is a kind of a repeat of the same thing. Here we want to emphasize that the energy consumption in data centers projected by this particular study is that roughly 8% of the total energy consumption worldwide would be in data centers. And with AI, this is becoming very much visible because there are a few important predictions which say AI will be consuming more power, more energy than the human workforce by 2025. Again, China has a prediction that they will consume 4% of their energy in data centers. And in all this, these interconnects, data movement and interconnects are becoming the most important part or extremely important part. Okay, I hope I'm audible. Okay, so energy efficient interconnects are needed, and that's the key objective in this work that we have done at IIT Bombay. And also this session, we are focusing on this. Again, like a lot of this thing has been covered, so I won't spend time on it. But the idea is that these modules are going to be used in big numbers, and their usage is growing exponentially. This thing again was covered for shorter distance interconnects in the data centers, within the data centers and across data centers. IMDD PAM4 schemes are being used, and beyond certain distances, coherent schemes are being used. And as we move further, co-packaged optics is going to be used, at least for the AI applications. So this was again an introduction. What is the difference between intensity modulation direct detect versus coherent? The main thing is in intensity modulation, we just modulate the amplitude of or intensity of light. And for coherent, we modulate the amplitude and phase of the electric field. In this case, the problem in coherent is that the carrier is needed. The carrier FC, right? So that makes it much more challenging. Actually, coherent was tried in 1980s, but then people went with intensity IMDD scheme because recovering the carrier and aligning the carrier of the transmitter and the receiver was difficult at that time. Now with electronics, it is possible. So summary here is that with IMDD, the power consumption and cost is low because you don't need to recover the carrier, but the capacity is lower and the reach is shorter. And for coherent, it's the opposite. So when we started research in our group at IIT Bombay, with my background, my focus was, can we make coherent energy efficient and low cost? So, so this is a typical coherent transceiver. You have a transmitter here, IQ modulator for 100G, and you have a receiver here. And let me see if I can use a laser pointer. Okay, leave it. So we have a transmitter here and a receiver here. So what are the major challenges in a coherent receiver? First is the optical channel impairments, which include primarily chromatic dispersion and polarization mode dispersion, which rotates scrambles the polarization of the signal, and it also disperses the electric field, adds dispersion in the electric field, chromatic dispersion, which is frequency dependent. And the other part is the laser phase noise. The transmit laser and receive laser, they are independent and they have to be aligned in frequency. For that, you need a lot of very precise temperature control for that alignment. And then you have to do some extra processing in the digital domain, in the electronic domain. So that makes it really very expensive solution. As well as you have extra DSP involved, extra power consumption because of laser temperature control. So we need, as I mentioned, low line width lasers with tight temperature control, and the burden is on electronics to recover the data. In our group, way back in 2011, 2010 or 11, we started this activity. This work was our first publication in this area. We suggested that we can do this in analog domain. The advantage is you don't need ADCs and you don't need DSP. And with analog, you can provide faster feedback. So this can be quick. This is doable. For shorter distances, it makes sense. For longer distances, the equalization required cannot be taken care of using analog approach. So our first comprehensive paper on this was in JLT 2015, where we showed with chip-based, extensive chip-based simulations that we can do both equalization and carrier phase correction in analog domain. It was initially difficult to convince the community that this can be done in analog domain, because typically for coherent, people would always visualize it as a DSP-based approach. So we were able to demonstrate our chips in OFC 2017 and 2019, and there has been follow-up work from other universities as well in the same area. So now with this analog approach, now it is also being considered for these switches, where the idea is the modules here instead of using the DSP in the modules would just use linear direct drive and retimed links, and all the DSP is on the host IC or the switch IC. So that saves a lot of power. Of course, this discussion is not really in the context of Coherent, but same thing with our technique. Coherent also supports it. It can support Coherent as well. So now another important part that we realized, this Coherent carrier phase correction was not easy, right? So we also came up with a scheme where we can make Coherent much simpler. So the main problem was the frequency mismatch between the transmit and the receive laser. So what we proposed is that we send the carrier in one polarization and the signal in another one. So actually this approach, it was not new. This has been proposed by people earlier, where you can see that this horizontal arrow represents the modulated signal and the vertical represents the carrier. Carrier is typically much stronger than the modulated signal. So this approach had been proposed earlier, but it was not considered as a practical approach, because at the receiver, there was no easy way to separate out the carrier and the modulated signal, because this carrier and the modulated signal get scrambled because of polarization, rotation, and PMD. So we came up with a technique where we can use a very simple power minimization algorithm, where we measure this power and ensure, like using a feedback loop, we polarization. So with this approach, we can now use Coherent for this short reach interconnects. Of
Dr.
course,
Gupta,
we lose one
around
polarization.
3 minutes.
We lose one polarization here, but still this scheme turns out to be better than IMDD, because it doubles the capacity versus IMDD, and we are talking about short reach interconnects where we are really competing with IMDD. So in all practical aspects, actually, I would also like to mention one thing. So this scheme we demonstrated, and then it was actually revalidated by Huawei group as well. So in overall, the advantage over conventional Coherent is we can use uncooled laser now, because the laser that we are using for the modulated signal, same laser is also being used for the local oscillator at the receiver. So even if it has more phase noise, even if it is a lousy laser, it still works. So we can use uncooled laser compared to the conventional Coherent scheme, which reduces the power consumption cost. It supports linear, unretimed direct drive pluggable modules. Versus intensity modulation, it doubles the capacity. It is more dispersion. In general, Coherent is more dispersion tolerant. So it is more dispersion tolerant. So overall, because of packaging costs, and it also provides a larger link budget, so it can support this optical switching approaches that Google is employing, because it provides extra link budget. So with all these advantages, it is actually significantly better approach than IMDD, and for shorter distances, Coherent, the conventional Coherent as well. And there was a question about this 3.2 Tbps modules. Up to 1.6 Tbps modules, they have been defined now in the community, in the standardization bodies, more or less. But there's a big question mark about 3.2 terabit per second modules. So this scheme can achieve that. So I would like to get a feedback from Dr. Radha if he's still listening to this talk. But according to our view, this should be achievable. 3.2 Tbps solution is possible with this approach. So I'll not go into this details comparison, but basically, if we compare with IMDD in all aspects, it can turn out to be better. Of course, these are comparisons. All of them cannot be achieved simultaneously, but If we keep some of them constant, for example, let's say if we keep the cost constant, we can achieve better reach, and we can achieve better power efficiency and things like that. So overall versus IMDD, this can always be a winner.
Would you show the summary? Yeah, thank you so much.
So this is the summary slide, which shows the typical for conventional coherent schemes. They are good for very long distances, but they consume a lot of power. IMDD schemes are good for shorter distances, but they still consume more energy compared to the our approach of PMC SH coherent, PMC SH coherent. Of course, co-packaged optics does not involve long electrical interconnects, so it is much lower in power consumption, but these schemes can also be extended to that. This is another experiment we did with
for the
Starlight.
interest of
This is
time,
the
shall
last
we?
slide. So this is another experiment we did with this 4-core fiber with PMCSH with the Starlight group. So I just showed this as an example. Yeah, thank you very much for your attention.
Thank you, Dr. Gupta, for like several insights into like using architecture to solve problems and going like instead of the conventional way, going beyond and looking at it in a holistic fashion. So in the interest of time, I think I want to thank you for this wonderful talk and small memento for.
Thank you.
I now request Dr. Deepa Venkatesh to join us on stage for honoring the session chair. Thank you. We are now ready to move on to our next session, which is a panel discussion on standardization challenges and solutions. I invite Mr. Rituranjan Mitar, Advisor and Head of Telecommunication Engineering Center, to conduct the session. I would also like to invite the panelists to the stage. Sudeepta Baumik, STL, Jishnu Aravindakshan from Tejas Networks, Radhakrishna Ganti from IIT Madras, Krishna Kumar from SASMOS, Gupteshwar Maji from CDOT. This mic is
So welcome to this session on standardization. Am I audible? Thank you. So it's indeed an honor to have a very esteemed. No, he's there. He is there. Oh, yeah. Okay, I would like to bring start the session with a small introduction of esteemed panelists. Professor Radhakrishnan Ghanti is currently working as Associate Professor, Indian Institute of Technology, Madras. He did his MTech in Electronics Engineering from Indian Institute of Technology, Madras. And then he took his PhD from University of Notre Dame in the year of 2009. He's presently expertising in communication networks, wireless communication and networks. He has over 31 journals, articles published, 32 conference proceedings, and 2 review, and many more achievements. Dr. Ghanti. Okay, coming to Mr. Gupteshwar Maji. He's MTech in computer science. His current position is group leader in CDOT. He's presently working in CDOT and has over 22 years of experience in design and development of optical products, which include GPON OLTs, ONTs, 100/200G WDM systems, OTM cross connects. He's also involved in standardization because my organization TEC deals with standardization. I see him in various his active participation in various committee meetings. He's also a vice chair in Telecommunication Standards Development Society of India. So welcome, Gupteshwar. I'll now move to Mr. Sudipta Bhaumik. He's a postgraduate ceramic engineering from IIT BHU with over 25 years of intensive experience in various positions related to quality management, manufacturing, application engineering, standard engineering in optical fiber and cable manufacturing industry. He's presently with Sterlite. He's also engaged in research on subjects of quality, reliability, application-related issues of optical fiber cable, and he has published over 40 papers. He is also a vice chair in ITUT Study Group 15, project leader of IEC, and he also participates in BIS Sectional Committee on Fiber Optics, and he's liaison officer between ITUT Study Group 15 and IEC TC 86. A lot of standardization depends on the liaison between various SDO, Standard Development Organization. So that was his one role of liaison officer. He's a 2-time recipient of Urbane JH Mallow Medal by Wire Association International, Boston, USA, for the best technical paper. Welcome, Sudipta. Krishna S. Kumar, Professor Mr. Krishna S. Kumar is Head Technology, Samsung HET Technologies Limited. He has over 25 years of experience in the development of photonics products with applications in telecom, defense, and medical markets. Prior to this role, he co-founded and led innovative photonic product companies. He has over 10 patents in optical and medical devices. He holds an MSc in physics from University in Hyderabad. Welcome, Krishna. Jishnu is principal architect technology in CTO office, Tejas Networks Limited, and has 19 years experience in the field of telecom. He did his BTech from NIT Calicut, MTech from ISC Bengaluru in 2004. He joined Tejas Network and is responsible for deciding the long-term roadmap of the company. He has represented ITUT in Study Group 15 and has contributed towards the development of ITUT G8032 and MPLS TP standards. His present interests include 5G Advanced and 6G. He's also involved with TSDSI and also an individual member at 3GPP RAN I/SA2. He was closely associated with the design of 3G and 4G backhaul network for national as well as international operators. He was also a key person who led to the inclusion of low mobility, large cell use case in 5G evaluation. Sorry. So recently, as part of Indian delegation, he represented in ITU our meeting in Geneva, and it was quite a successful meeting. We'll later come to that. He has filed 18 patents and was awarded the best paper award by IIT in 2006. He has edited the Springer's CSI transaction on ICT on a special issue on wireless in the future as a guest officer editor in March 2019. So welcome, Jishnu. So it is indeed a pleasure to be chairing this session on standardization. Just to begin with, to set the ball rolling, let me explain about the organization I come from. So Telecom Engineering Center is an attached office of Department of Telecom with three basic responsibilities. The first is standardization. The second and third are testing and certification. It is these roles as testing and certification and standardization as a front end for ITU-T, in International Telecommunication Union standardization sector, that we also contribute towards standardization through what is called a national working groups. So ITU-T standardization is done through in a broad 11 topics in various technology domains. I'll not go into all the 11 topics, but so the corresponding to every topic, Telecommunication Engineering Center has a parallel arrangement, what we call a national working group. So if it's a study group 15, which deals with optical fiber and cable systems and optical fiber systems in ITU-T, so we will call in TEC a national working group 15. And we are also supported. This national working group has experts from industry and academia, and other individual experts, maybe from telecom operators. And together we regularly meet and discuss on what we call Indian contribution to the ITU standards. So through the national working group, this is the effort, Indian effort led by TEC, but in an active collaboration with academia and industry. Most of the panelists are participating in TEC, as well as they're also participating in TSDSI, which is another society of the DOT meant for promoting. For example, if TEC represents Indian interest in ITU-T, TSDSI is one of the organizational partners in 3GPP. 3G partnership project, which is responsible for standardization of not only was 3G, 4G, 5G, and also will take care of 6G. So, and 3GPP and TSDSI also takes care of as a front line organization from India for the 1M2M. All the IoT standardization is actually done, a lot of it in 1M2M. Of course, there are multiple SDOs. In any topic you take, there'll be multiple SDOs which will be spearheading the standardization effort. So now I'll move to the panelists. But before we move to the optical fiber and the optical transmission system standardization, I'll first like to ask Professor Ghanti, having a vast experience in 5G standardization, that how was the Indian contribution in 5G standardization, and how do we really go forward in improving that participation, and what are the key learnings there?
Hello. Thank you, sir, for having me on this panel. As sir pointed out, my background is in wireless, so I'll give you just a wireless perspective of what happened in 5G. So when we started the standardization activities 5G in both ITU and 3GPP, the Indian delegation was very small delegation. I mean, the contributions from India to both ITU and 3GPP, but specifically in the technology area, were very few. The main reason was that the Indian industry at that point was not mature enough. So a lot of this was work was being done by academics and government agencies. So when we initially went to ITU with this idea of large mobility, large cell for coverage, there was a lot of reluctance from the international bodies to accept this thing because one was that they did not know if we were serious enough, in absorbing, in making this kind of technologies for the global arena. That's one thing. And the second thing is, they were, one of the questions that they had was, is there industry in India to build these products? So we had a lot of difficulty, but fortunately, there was a lot of push from the government, and there was a coherent push from academia and industry. I mean, Tejas and STL, all of this were involved, and we were able to push at least the requirements of India in ITU. And so afterwards, we followed this with a lot of technology work in 3GPP, where we were able to, where India was able to actually, most of you might not know this, but India had another standard called 5G-I. This was the only other standard other than 5G, which was ratified by ITU as a IMT 2020 standard. So a lot of background work has happened on this. And fortunately enough, all this got accepted by ITU. So what were the lessons that we learned? Okay, so it's a long-term commitment. Anything that if something has to go into a standard, it's not a 1 year or a 2 year, but it's almost 5 to 6 years of work has to be done. It's a consistent work. I mean, you require champions for that. You require support, institutional support from both the institutions you are working in, government, industry. A lot of things have to go together. And before all that, as a nation, we should have a goal that we require to get X number of contributions into this particular standard. We should own about 30% of this standard. If once we have this vision set, I think there is enough maturity as well as enough experience in this across various domains that we can make this happen, sir. And I think in 6G we have started very early. I mean, this is one of this forum. I mean, you see all this happening even before 6G started. I'm pretty sure that we will have a resounding success. I mean, yeah, thank you, sir.
Yeah, so thank you, Professor Ghanti. So as he very clearly said that when you go there, it's an exclusive club. They really want to know whether you are serious or a long-term player. So that was one of the key message. Other thing is a long-term commitment. Otherwise, if you go there or participate as an observer, then we can do it. But if you need to get the Indian standards or our own contributions in, it's a long commitment that is required. Now I'll turn to Mr. Jishnu. He has also a lot of experience in the ITU-T study group 15, which takes care of the optical this thing. But before that, since you have participated in 3GPP also, you have also participated in ITU. So can you just tell where are we in terms of standardization in these organizations and how do we improve there?
Thank you, sir. Thank you for inviting me. The first thing is that there is a big difference between ITU-T, which is related to optical, versus ITU-R. ITU-T does all the work within that organization, so it doesn't outsource it like what happens with ITU-R. ITU-R actually makes the question paper, and then the actual standardization happens in 3GPP. ITU-T does both the work in the same organization. So that's one good advantage with optical. The one thing which we learned also, like we initially were contributing purely as Tejas Networks in ITU-T. It's much more impactful if you go as a country, if you go as a team, because it needs a lot of coordination across countries, because in ITU, basically, if you have two countries opposing something, you can completely stop the work. So it's more about countries working together rather than institutions working together. That's why one of the reasons I heard it was eventually moved to 3GPP, because it's far difficult to get things at a wireless level done in ITU-R. But in IT/UT, most of the work completely happens within the organization. The second part is like, it's good to see in 6G, we recently did the initial work of adding a completely new usage scenario called ubiquitous connectivity. And one of the aspects of ubiquitous connectivity is that there is an understanding now that if you have to do ubiquitous thing, it cannot be done only with terrestrial wireless network. We need to consider other non-terrestrial aspects, including fixed optical network, satellites, and even HAPs and other things which are coming up. So there is an issue of interworking, which should ensure that all of this interworks. So I think as part of the AOC work, I think that could also be standardized along with, so it's no more wireless, and I hope 6G is more about convergence of wireless and optical, because even I see some of the modulations being discussed are more or less same. OAM is being discussed for terahertz, and I think once you move to terahertz, it's more optics rather than RF. So that's one good thing, and one great thing which has happened, I think, under Mithar sir's thing is that we are working as a team. So this is first time I am seeing we have no other background work which we need to do and all that stuff. The NSG, NWG is working perfectly fine. Academia, industry is collaborating. We need to also take care that, I always say this to Radha, is like, sometimes I find that this is like a game of chess whereby some of your own pieces are misbehaving. So that we would have to take care. So that I think is something which we both learned in quite a different way. Other than that, it's all fun. It's like, I think I hope a lot of optical contribution comes in. And in study group 15, it's much simpler. It's not like ITUR. So hopefully we'll have a lot more of those standards this time.
So thank you, Jishnu, for explaining what is ITU, what is 3GPP standardization, and how industry, academia, and the government agency, the TSGSI, we are working together as a team and taking forward the Indian interests. Just a minute on more on ubiquitous connectivity. It was a big win for India very recently, because if you see the 3GPP standards for 4G, 5G, the coverage as such is not very clearly specified. But for the first time, through the usage scenario in the 6G framework, the usage scenario related to ubiquitous connectivity, we have been able to put coverage as a metric. So this has happened for the first time, and there was quite a bit of opposition, because any OEM will not like their equipment to be subjected to a coverage test, because they very kind of argue that, okay, it's a deployment scenario. It's not a scenario that you can fix a distance for the radiation from the BTS. So it's again, he mentioned about chess pieces. See, you go to an international organization, you go with 10 proposals in a contribution or in a set of 2 or 3 contribution. There it's the standardization is all about collaboration and consensus. And consensus, sometimes you need compromises. So that is, you have to be ready to do it at the last minute. There is a system of, the consensus in ITUT is so very important that they will immediately halt the meeting in between, and they'll say, okay, let's take a coffee break, and let the main proponents or opponents of a particular proposal or a particular para or a particular phrase even decide outside. And if they decide, and then we can, obviously the whole meeting formally can agree. So there is a system of consensus. So when you have to walk that path, you need to make some compromise, but you have to be very clear what you will compromise and what you will not compromise. So it's a very well said, it's a teamwork. And the Bharat 6G vision was launched about 15 days back by Honorable Minister, and he has given a very clear target for the country in terms of 6G patents, 10% of patents. So patents, and of course there's a session on patents tomorrow, I think, and standards also are a very important part in that direction. So, so thank you, Jishnu, for very well explaining that. Sudipta, now you are have a long experience in optical fiber industry. You are also a leader in your own company, Sterlite. You also are a vice chair in ITUT Study Group 15. Can you tell where are we in terms of now optical fiber systems standardization in Study Group 15? Where are we and how do we further promote? There are a lot of young minds here. How do we incite them to contribute to the effort that you are leading from India in ITUT?
Thank you, Chair. The Study Group 15 ITU deals with transport, home and access networks. So all these optical components that you find all comes under Study Group 15. And actually my journey and my company journey starts in ITU in way back in 2007 when we got the sector membership of ITUT. And the sector member is the second highest level of membership in ITUT. First highest level is the member state, that is, of course, the Minister of Communication, that is DOT. And second highest level of membership is the sector member. So since 2007, we have been contributing in different standards, mainly in the optical fiber, cable, components, passive hardware and passive infra, kind of all the structures. And here also I want to mention that National Working Group 15 is playing a very important role in India-specific standards, which is a mirror committee of ITU Study Group 15. So we are sometimes directly contributing to ITU, and most of the time we going along with the National Working Group 15 to give the India views and get the view of all the members of the National Working Group 15. I have to give you one example that in the recent years, we published a new ITU standards called L.209, that is fiber optic network termination box. And this is originated from the Indian contributions from National Working Group 15. And that was the box which is basically accommodate both active and the passive instruments, which is a unique to Indian scenario. And that box is used in BharatNet project 1 and 2 exclusively. And so that was one of the major standard that we published from India in the ITUT's Study Group 15. Other than Study Group 15, we have another important standardizations SDO in fiber optics domain, that is IEC, International Electrotechnical Commissions. TEC is the mirror of ITUT, similarly BIS, that is Bureau of Indian Standard, there is a mirror committee of IEC. So IEC, TCs have a mirror committee in BIS called LITD 11 that we deal with all the fiber optics components. So also we are participating in the IEC CCTC's committee on behalf of BIS, because we do not have any direct membership in the IEC, you have to go along with the BIS only. So including ITU Study Group 15 and IEC, I think so far you have contributed almost over 80 international standards. And not only the contributing, also we are taking a lead role in different editors, we call in ITU and project leader in IEC. So we have around 10 standard we are leading either editor or the project leader. In IEC, there's another kind of membership we call O member and the P member. O means observer. That means you can just go and see what is happening there. But you have really participate and you have to contribute, you have to become a project leader in any standard, you have to become a P member. So in the P member also, you have, and to get a P member, you have to really show your technical expertise to become a P member. So in Sterlite, we have contributed to developing one of the new technologies in fiber optics called low diameter fiber. And when the development happened, we send a contribution from BIS, and this helps India to become a O2P members. And then you control the P memberships by continuing, by contributing all the technical committees. So this is the brief about the contribution from India, mainly the optical hardware point of view in IEC and ITU.
So thank you, Sudipta. It was a very informative intervention in terms of what BIS does and what TEC does, and the corresponding difference between what IEC and ITUT does at the international level. So the next question will be to you, for you, Gupteshwar. So as now CDOT is a government of India society leading the R&D efforts of on behalf of Department of Telecom in the space of various products that you have. So there is a great expectation because R&D and standardization are very close to each other because as the many panelists have said, that you need to prove your technical expertise. You can't just go and you can be observer, but if you want to really contribute, each and every phrase is thickly debated. So you cannot stand if you just go there as a woman with a little level of knowledge. So what I would like to ask is, what are the efforts of CDOT in terms of standardization in the optical domain? I mean, you have a lot of products, we know, but what special efforts is CDOT making in this area for the standardization?
Thank you, sir. Thank you so much. CDOT is being a part of, is audible? CDOT basically a R&D organization, and this is part of government's perspective of doing R&D for people of India. So what is our role and how do we deliver that part? Basically, CDOT works on many technologies. Like we are also working 4G, 5G, but let's speak about the optical technologies over here. So basically, as a product, we work on WDM, OTN Cross Connect, GPON line of products, and we do R&D on that one. Particularly in hardware domain, we have a separate team. In software domain, we have a separate team. So, starting from product, thinking how it would be in the field, the requirements till the, the product going to the field, we have in all phases of the product design, we build systems. And of course, we go to field with a TC, there are GRs, general requirements. We need to meet the GRs for the product to be put into the field. Simultaneously, we take care of the things that what is happening in international areas, in I2T, for 3GPP, what is happening over there. So as part of standardization, because the government has mandated TC for making some standards so that the products which is going to the field would meet certain standards. Simultaneously, TSDSI in another organization which makes standards and for Indian usage. There are international usage standards, and we actually build Indian standards what we can that can be put onto our systems. So I was working with Jisnu that time as TSDSI. So we thought like CPRI to be one standard. We want to map CPRI to OTN. Normally they used to put in IP over WDMs, or they were not in a concrete thought process that they will put it on OTN. So we discussed amongst ourselves, why not put onto this onto OTN mapping, CPRI to map onto OTN. So during that process, I learned many things, and actually that can I share to you, because the process of standardization, we started thinking to put it onto OTN frames, and Jisnu he took the lead, and from our side, I was actually kind of a reviewer for him, giving comments or analyzing what if anything is missing. So I was giving input to him, and when he came up with a draft, we put it to people for giving their inputs. So there were positive comments, and there were something like that, whether this can meet some standards, particularly latencies. So we have to prove that this can actually go to the field, satisfying the latency requirement also. So in that took a little bit of time, and that took a little bit of challenges for us also, because we were thinking whether, we can go ahead with all our, what you are suggesting. But in the process, we had to, experiment many things to make them satisfy. So I think we got a first, standards from DSD at that time. So I would suggest that you go on, experimenting, prove people, get comments, and then go for standardization. And from CDOT perspective, right now we are working on this AOC test bed. See, this AOC test bed, it should not be just a test bed, people putting their things onto this one. This would use as a standardization platform so that interoperability can be tested. So many people coming with their software and hardware solution should come onto the platform and then makes that it works and works in a standardized fashion. That is what the intention of this AOC would be. That's what I think so. Thank you so much, sir.
Thank you. So, so Gupteshwar, you raised a very, very important point of field experimentation. So field feedback is also gives ideas to the developers. What is the requirement of the network operators, whether what they envisage in the lab, whether it's working like that or not. So thank you, Gupteshwar. It was a very important factor in part of overall. In fact, if you go to many standard development organizations, it's not the OEMs. There are many international operators very active in those standardization bodies, because they may say that, okay, out of this effort, I want this performance sometimes. So operators also are a very, very important part of standardization ecosystem. So thank you, Maji. So we are here actually for the workshop on advances in optical communication. So Krishna, what I would like to ask you is, now this test bed will kick off. So what are the steps we should take in terms of standardization so that the learnings from the advances, these new infrastructure that will come up, this also translates to our participation or the increase in Indian participation in the standardization domain.
Okay, thank you for the question, sir. I think right at the outset, there should, I think we all should agree to have a strategy of each of the programs in the AOC to evolve a standard in the products that are being developed. I think, like you mentioned, where there should be a team consensus, and also so that include the SDOs right at the beginning of the projects, and to make aware each of the project leaders, what standards should be developed for the projects that are being envisaged. And it is, one of the projects is about Li-Fi communication. It is very good to know that just about last week there was a standard that has come up for the Li-Fi from IEEE, and it was not there earlier. And I think in maybe a couple of other projects where they are really not an agreed standards, maybe like the multi-core fiber, I think that part is still being debated, and that development is part of the AOC. We should probably look at, what kind of standardization needs to be looked at in terms of the diameters or the number of cores or the crosstalk that needs to be there. And I think, Sterlite is probably right up there doing that aspect. And, with me coming from the radio over optical fiber technology, I'm really keen to understand that what, standardization can be applied so that it can meet all the 5G and really in the future for the 6G going into the very high bands. Apart from the Li-Fi, there is also another project on free space optical communication, right? And for which I don't think there is really a standard. Please correct me if I'm wrong on that. But it has been debated for many years, how to deploy this and where it can work. But now that Li-Fi has come for the short distance, maybe something can be evolved for a long distance, free space optical communication. So I think, we've discussed this with Deepa right from the beginning that yes, it is very important, like how they mentioned, that teamwork and for companies to have a strategy when they are developing this product on how to meet the standards so that, these products can have the global exposure. That's probably the most important part of being, standardizing the products to meet the global market. Thank you.
So thank you. So Krishna raised a very important point of awareness and education. In fact, on the 7th July, we had a national workshop. We had a national workshop on standardization in CDOT Delhi. So in one of the panel discussion there, one eminent speaker mentioned about his efforts for education. And I think our own organization, DOT, which specializes in training, NTI PRIT, we are talking to them also to how to increase the training effort of how to handle the whole work of standardization. Of course, there is nothing to beat a long-term commitment of any organization. So that is there. But just to give a beginning, of course, there was a suggestion that whether some of the all the students do a lot of projects in the academic institutes. So whether giving them a standardization project, a part of it should be a way forward to get their involvement, because we need to increase our effort. When we go to ITU, we find that there are a lot of academic institutes also there in good strength, participating meeting after meeting, years after years, just to get in the thick of things. So a long-term commitment, though, is important, but yes, point well taken. Your query about FSOC, I think there is no standard yet. Of course, there was a field trial done in Meerut, I think Nagaland, and one more place by Google Tara. Their product was Google Tara. 3 places we tried. One of the Indian companies, which is based in Ahmedabad, Navtech, they showcased FSOC in the last IMC in Pragati Maidan. So there they have a system. In TEC, we are evaluating that system. I think, yeah, okay, you need to.
Yeah, just one is recently, I think, Study Group 15 in question 6, the one new topic is initiated to develop a standard on the space optics. And there's a contribution from the National Working Group 15 as well in the last plenary meeting. I think Mr. Rakesh Desai, who is the chair of the National Working Group 15, is here. I think we can discuss with him. Maybe we can submit a new contributions to this new work that we are doing in ITOT.
Yeah, thank you. Thank you for that. Yes, of course, you said Mr. Rakesh Desai, who is the National Working Group chair from TEC. He is here and you can meet him. But just because he raised the question 6, I would also, for the benefit of audience here, the whole ITU work group is categorized in questions, and every question has so many recommendations under its fold. So I would like to just, for the record, of course, everything is available on the net, read some of the important questions that Study Group 15 has. So the question 1 is coordination of access and home network, transport networks. Question 2 is optical systems for fiber access networks. Then question 4 is broadband access over metallic conductors. Then there are so many. Question 12 is transport network architectures. And just to inform you that we also have now, on the 7th of July, we launched a portal which is called Standardization Coordination Portal. So I'll request all those who want to participate. It's a very easy way through the Standardization Coordination Portal. You can become a member of that portal and you can choose the national working group of your interest. And just to tell you that though TEC was earlier focusing on ITUT, now we are mapping the IEEE study items onto the national working groups so that we can really converge the efforts of the various bodies. But that brings in my mind to a very important topic, that there are multiple standard development organizations for the benefit of young minds here. Sudipta, can you tell your take and how to harmonize? I mean, when a student decides, okay, I want to approach, I have a contribution, I can do it. So which body does he really go to? Can you throw some light? You have experience on IEC, ITU, TSDSI within.
Yes, I mean, when we really wanted to standardize the outcome of the research, because ultimately the standardization is a bridge between research and the market. Without that, we cannot go to the market. So the first of all, you have to see that which bodies are really working. We have every questions, every study groups are there. One chapter called motivations in ITU, and in IC called scope of work. And if we go through the scope of work at the motivation chapters, then we understand that which areas this particular working group or study group are in. Then you have to align your research work, after research work, along with that study group work. Then you can submit your contribution either in IC or IEEE or ITU. Regarding that harmonization of the effort of all these study groups, there is some overlap is always there. But again, to harmonize the effort that I already mentioned before, that we have a liaisoning activities in different SDOs. For example, ITU has a liaison reporter or IC has a liaison officer. For example, I am the liaison officer or reporter between ITU study group 15 and ICTC 86. So my duty is to report whatever thing happening in the ITU to report in IC meeting. Similarly, whatever happening in IC meeting is report to ITU meeting, so that all the experts in those different communities, I mean, most of the experts are also common both in ITU, IC. They can know each other and understand the work they are doing. Other than liaisoning report, we have a one more channel called liaisoning statement. So after each and every plenary meeting, the study group or in the technical committee in IC, they issue a liaison statement to other study groups. Maybe it is maybe within the ITU also. For example, study group 15 can issue a liaison statement to study group 11 or study group 3 if they see that some work is overlapping to each other's. And that liaison statement either for information or for actions. So this is a communication channel between the two SDOs or two study groups just to harmonize the effort of the activities. So this mainly that we are doing to harmonize. Same thing we can follow in India as well. We have two different standard organizations. We can have a liaison positions. They can participate both the organizations, and we have a channel to communicate.
So thank you, Sudipta. Just one last quick question, maybe to Professor Ghanti first. There was a talk of long-term commitment you only mentioned. So coming to your team in IIT Madras, your take on how to build that team very quickly, if you can, because I need some time for the question answers also.
Okay. So there are two parts of any standardization. One is understanding the process, and the other is actually the technical contributions. So if you want to be successful in standardization, the first thing that you should do is attend meetings. Okay, even if you don't contribute anything, the first 4 or 5 meetings, your team of 5 people or 6 people, just go attend, understand the process. All this ITU and 3GPP, I mean, are old organizations, so they have very well-defined process. Understanding this itself is a big exercise. Once you understand that, then you will have a sense of comfort, and then you can start contributing to this technically. So the way we do in my group is, for the first 4 or 5 meetings, I don't expect any contributions from the students or the postdocs who attend these meetings. They just go, they try to understand how do you submit a simple document, how do you understand where to read the document. From there, at that point, they'll also start understanding what other companies are doing. And in general, what happens in my group is that we try to align the research a little bit. I mean, research specifically for a PhD student, fundamental research is very important. I don't expect them to do standards work. I never expect them to do, but at least align a part of it towards the standards and then slowly start contributing. And there are, and we have senior people who help them in making sure that this translation to standards is also easy. That's also important. I just want to add one more point specifically to the AOC group. There are global standards, there are Indian standards. India is a big market. If you feel that you can come up with a technique or a product which is not aligned to the global standards, but we have a upper hand in marketing in terms of deployment, we should go for it. Okay, specifically, for example, when you're making QSFP adapter, I mean, I'm pretty sure that the QSFP market in India is so big, but if you feel that we have a specific technology that can serve all these requirements, but it's not aligned to the global standards, I think as India, we should go for it, make our own standard, and then slowly nudge the global things to align with us. I think that's the way we should proceed further.
Yeah. Thank you. Thank you, Professor Ganti. Maybe Jishnu, your take on what Tejas is doing, and then we will call for questions, please.
Yeah, thank you, sir. So basically, yeah, I think as I mentioned, wireless and optical is converging. So though we speak a lot about wireless in 6G, finally it looks like it's like a street light would be all the wireless and all the behind thing would be optical. So though like from a standardization perspective, wireless takes the lead and optical has to follow, but it's not going to be in 6G. I think the optical should be basically requiring a lot more standardization, because now we are taking the components, everything all the way towards the street lights. So all of that things should work. The other thing on what Radha mentioned also, especially on the interconnect, interconnects are usually between what we call at least in Tejas, we call it as leaf and spine. So the leaf and spines are both made by the same company. So you just need to standardize within India. You don't need to even work with outside, etc. So there are some areas which even FSO, for example, these are all book-ended solutions. So this could be something which can be standardized in India. Things which are like submarine cables, if you have to QSFP or any other higher speed interface, 800 gig, GBPS, etc., you would need to work through ITU. So that could also be done, whereby some of this could be standardized in TS, TSI, TEC, etc., which can be completely for Indian specific thing. And this is just because both Tejas and CDOT can, for example, use the same interconnect. We don't need to do it. And that itself is a good enough volume for any person to do it. Same thing with what SASMOS is doing with respect to the RFOF, because this is purely between the RU and this, and it's completely an internal thing. Both Tejas and CDOT can use the same thing. But things which are like optics, which are long distance thing, has to be standardized through ITU. So I think there is G709, study group 15. So more or less all the optical thing can be done in ITUT study group 15, and corresponding thing is NWG 15, through which I would seriously suggest we go through as India, because as an India administration, we get much higher respect compared to going as an individual company. So it also helps to evangelize this within multiple companies in India, so that we don't also make that mistake. So we also understand it and then take it to the standard. So I hope a lot more of those standard work happens this time from optical.
So thank you, Jishnu. So I think we will take some questions. Madam, I hope we have a couple of minutes for. Yeah. So any questions on the topic to any of the panelists, please? Yes.
Indian version of standards getting global. So maybe Sudipta, you may. So, for example, we would be working on developing indigenous technology, especially under AOC platform. What kind of challenges you are facing at the ITU or IEC, especially if any standards initiative is coming from India, and what support you would be requiring, including government agencies as well as industry? Any of.
Yeah, so one thing, say for example, I was yesterday part of the RFOF work which AOC is doing. So in wireless, we have something called a position reference signal, which is basically you have to ensure that your phase and time are perfectly, because the biggest thing in 6G we are trying to do is, can we get into much better accuracy, less than centimeter, if possible, and which even today the GPS cannot provide. So this would need optical, but it has two parts. It has a wireless part, which basically has a PRS signal. And then there is, if you're carrying it over RFOF, we have to ensure that the phase are not changed. And if you have a cable, for example, a multi-core fiber, which is there, all of these issues need multiple level of people who are different expertise. It's not like all of them would have expertise on all of this. So issues are like academia needs to really figure out what are the issues if suppose the PRS signal goes over a cable, which are MCF. Maybe Sterlite can provide on how much would be the phase shift which happens in MCF. And similarly on RFOF, if that signal gets transmitted over say 2 kilometer, 3 kilometer, are there, I think there's called walk-off or something between the polarization, which can affect this. So all of these are completely unknown. So none of us really know what happens, but we know that finally we have to meet an accuracy of less than a centimeter in position. How do we do this? Needs to be split up across multiple things. What is the allowed tolerance at each level? And then maybe we work around it, and that would need some coordination. I think there is a separate OAM work which is happening on the multiplexing part of it. So we would need a lot more of those coordination sessions, maybe where we discuss. It's not no more a optical only problem which is being handled by a separate team and wireless handling a separate thing. Both of them has to coordinate, cooperate, and it needs industry, academia, and government to come together, especially from the standardization perspective, to get this thing done. And why standardization is quite important is, yeah, we want to sell in India, we want to make products for India, but we also want to sell it globally. If we could get something in standard, as Sterlite was mentioning earlier, we could sell globally. And I seriously see that's much larger opportunity because we can't be dependent on one country to make a product because it should be globally acceptable. And telecom is one field where you can't be making something completely like, it's not like you can make an Apple phone, iPhone, and then forget about standardization, etc. We have to work across different interfaces, etc. So all of these are needed. This is a perfect phase where government, industry, and academia has to coordinate. Everyone has their own strength, and maybe I would suggest that we do a SWOT analysis of each of our capability, and that would be the first step to take this to the next level of what each can do, what are our limitations. And that would, once we align all of that, then I think we would figure it out how each of them can help each other group.
So thank you. Any other question, please?
To add up your questions you asked, no, I want to extend Jishnu's point. Basically, more discussions are required. In AOC, basically, many people are coming for testing, maybe for testing purpose. But before testing, we need to standardize what we are going to do. So people who are participating in AOC must standardize what we are actually going to do. So everybody can participate in maybe in TSDSI or in government meetings that what we are going to do, what are the interfaces we need to define in a standardized fashion so that everybody builds systems based on those standardization only. Yeah. And government would support from that perspective that they are going to deploy in at least Indian scenarios, and which can be we can go to international markets also. So that's my point.
Okay.
Talking coverage in ITU was good, our efforts, but technically we should see we are moving up and up in spectrum in terahertz and optical. But technically we'll be able to meet it, comply it. OEM says I can only make the equipment and deploy. Whether complying the coverage is his possibility.
Thanks, sir. So in the next generation standard, terahertz is an important piece of the puzzle, 6G puzzle. At least that's what people are talking about, terahertz communication. So terahertz communication will not be about coverage. It will be about data rate. So now when they define coverage, it will not be for a particular technology. It will be an aggregate thing. They will say that across millimeter wave, sub-6 and terahertz, together somehow you have to cover this area, including satellites. So that is the way they are going to define coverage. Even that kind of definition was not there till now in both ITU and 3GPP. ITU and 3GPP do not talk about coverage as of now. Okay, so the first step in saying that, okay, I mean, the first important thing that the India has done was saying that at least we should start considering coverage. We should say that whatever technology or a combination of this technology should ensure that a particular geographical area is covered with a certain level of, with a certain probability. That is what has happened in the last meeting, sir. It's not like terahertz is going to do this. I mean, it's very difficult. I agree with you completely on that. Yeah.
Okay, last question, please.
We have discussed about equipment level or component level standardization for optical communication related subsystems. So myself working with in ISRO in satellite communications, where the optical communications links are being inevitable to cater to this terrestrial based communications also. This is going to supplement those last mile network. So whether in AOC, we are going to consider this standardization for free space optical communication related subsystems, especially if we see US has their standards in SDA, for which all the partners are manufacturing optical terminals as per their SDA standards, specifically for intersatellite or satellite to ground communications. So do we have any plan to include this free space optical communications within the purview of AOC also? And one more question regarding the safety standards. When we work for free space optical communications, this laser safety standards are very essential. So whether we should include, because in IEC, there are standard guidelines for laser safety. So what is the standard in India that is not specifically mentioned? Actually, there is a very vague definitions. We go by some standards, but not strictly followed within the Indian perspective. So what are those plans?
Yeah, okay. First.
So in terms of the free space optical, I think we discussed that. And usually similar to the radio network, it is deployment or the scenario based. Yes, it would be good to discuss any standardization effort as part of the AOC. And I think, you can, come with your deployment scenario, because you're talking about satellite to ground link, and see, if somehow that can be also tested in the testbed. That is one aspect. And the other aspect that you talked about is the laser safety part. Laser safety is very clearly defined. The eye safety at what level, what wavelength, that is all clearly defined. And I think you also mentioned that it is not followed. So that is, that is a very difficult to handle. We have very high power lasers that are used in the defense for, destruction and other things, and even simple communication lasers. But there are very specific standards, and they are also evolved in terms of eye safety in all the different wavelengths. Yeah, that can be followed.
Okay, quick reply.
Yeah, just on that satellite thing, the inter-satellite link, which is actually being discussed as part of release 18 in 3GPP, that could be completely based on laser. That's the real thought process in LEO. So there, one issue is like, I don't think safety is maybe there, but not as important as it's there in the terrestrial case. So that is where lasers are being used. The ISL links can be, inter-satellite links can be, it could be standardized. I don't know as such whether AOC is looking into ISL part. On the free space optics, we have been working with one company you were mentioning about Indian Whale-Money, the technology is there. So they use us not laser, they use LED lights to do it, but it's a shorter distance, but can give higher things. So that I don't know what, there is no safety standard as such, but that also looks interesting in the sense, one of the issues which at least we are working with Whale-Money, like, see, one of the issue in India, these are all India specific issue. You get right of way permission from government, but the local guy will not give you the right of way permission for 1 kilometer, for example, because it may be his house or something. Can I use FSO only for that link, right? So such issues are there, even the protection, for example, right? If there is a fiber cut, can I use FSO? So these are very India specific problem, which maybe we can standardize in India and can work out. But in satellite, yes, this is an issue which I hope somebody from AOC team can mention whether ISL is also part of it.
Yeah, so thank you.
Yes.
So, so with this, I would like to close this session, and it was indeed an honor to really kind of have a panel with experts from academia, industry, R&D, again from the Sterlite, Mr. Sudipta, Mr. Krishna from private sector. So it was a very, very enlightened panel, and with this, I would like to also thank the audience for being patient and having some questions also for the audience, for the panelists, so that I hope it was a good session. Thank you.
With the session chair to please hand over the mementos to the panelists. I now request Sri Deen Dayal Toshniwalji to join us on the stage for honoring our session chair. Thank you all. We'll move on to the inauguration of the exhibitions. May I now invite Ms. Gunjan Dave, Member Technology of DOT, to come on to the stage and declare the exhibition to be open.
Good afternoon to all the dear participants. Since morning, we have been listening to some very interesting and informed discussions from our very learned panelists and speakers on advancements in optical communication. And one very important thing that has emerged is that we have to move towards sustainability and green technology in the optical communication technology. As also in future, this merger of maybe optic and radio is, it looks inevitable. Now and we also had some very interesting discussion on standardization, very important discussion. So now, as a part of this workshop, we also have one exhibition. So where we have invited all the participants from academia like IITs and industry to showcase their various products in this particular technology. And this gives them an encouragement and also give chance to other participants to have an interaction with the exhibitors. So now, without wasting much time, I'll just, I'm very happy to declare the exhibition open. So requesting all of you to please visit the exhibition and encourage the exhibitors and also be a part of the discussions with them. Thank you very much.
Thank you, ma'am. Now it is time to enjoy your lunch and get a glance of the exhibition. We have made arrangements for both at D6. So I request you all to please go one floor below and enjoy your lunch. Rest of the session will be held at the same floor, which is one floor below this floor. And we'll be back by 2:20 so that we can continue with our afternoon session. A special note, please note that you can be in the auditorium in the afternoon only if you are getting a degree from CS or EE department of IITM. We will have the convocation degree distribution event happening here in the afternoon. So be careful that you are not getting lost in the graduation crowd. And please make sure you come one floor below, the D6 floor, for the next half of the session. Yeah, the complete session will be in the D6, this floor just below this. Thank you.
Check. Check. கேக்குதாப்பா check. 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 Yes. Thank Some other laptop.
Hello, everyone. My name is Cristian Antonelli, and I'm an associate professor at the University of L'Aquila in Italy. So first of all, I would like to thank Professor Venkitesh for inviting me to present our testbed for space division and multiplexing that we deployed in L'Aquila. Unfortunately, today I was not able to join the workshop in person, but I hope that there will be more opportunities in the future. The reason why I'm showing the mini starting point of SDM was probably
check.
Hope you enjoyed the lunch. We are now ready to move on to our next session. Session 3 entitled as Advances in Optical Fiber Technology Beyond Single Mode Fibers. I extend my gratitude to invite the session chair, Dr. David Koipillai, professor at IIT Madras, to conduct the session.
Good afternoon, ladies and gentlemen. Welcome back. It is indeed an honor to be a part of this session, which is an invited session on advances in optical fiber technology beyond single mode fibers. This morning's sessions were truly interesting. Here are some of the takeaways that I noted down: that there is phenomenal growth in the internet in the context of data, growth in the mobile industry, growth in the wireless LAN industry, growth in big data with machine learning, both in the generation, transmission, storage, and retrieval. We are also seeing new computing paradigms, edge computing for low latency, cloud computing for massive compute power. And all of these are riding on the advances in optical fiber communications. We heard about innovations, both in coherent, non-coherent in optical communications, thereby giving us a platform, a global platform for these advances in other areas to drive on. So today we have a session where we will be having a look into the future to some of the exciting developments in fiber optic communications. It's a look ahead, several years into the future of R&D, both in India and around the world. And for this session, we have three very distinguished and accomplished researchers: Dr. Arvind Kumar Mishra from Sterlite Technologies in Aurangabad, Dr. Youngmin Chung from University of Southampton in the UK, and Dr. Christian Antonelli from the University of L'Aquila in Italy. The last presentation will be by video, Dr. Youngmin Chung will be by online, and Dr. Arvind Mishra is here. We welcome you, Dr. Mishra. So we are indeed very happy to hand over the session to our speakers and have them share their knowledge, expertise, and their perspective of what lies ahead. So please join me in welcoming all the three speakers. Dr. Arvind Mishra is here. And I will give a brief introduction to Dr. Mishra before he takes over. Dr. Arvind Kumar Mishra is currently Associate General Manager R&D for the Center of Excellence of Sterlite Technologies Limited in Aurangabad in Maharashtra. He received his MSc and MTech degrees from IIT Delhi and his PhD from the University College Cork in Ireland. He possesses over 2 decades of experience in advanced research and development, driving technologies in the area of multi-terascale transport systems in long distance, metro, GPON and NGPON technologies, access networks, fiber optic sensor technologies and systems for security and smart infrastructure. Prior to 2012, he worked for 12 years in Europe, primarily in Netherlands, Ireland, Greece, and Germany. He has published over 65 articles in peer-reviewed international journals and conferences. He has also served as the president of the Fiber to the Home Council of Asia Pacific. We're indeed honored to have him here with us. Please join me in welcoming Dr. Arvind Mishra for his invited talk.
Me to talk about what work we are doing actually here. So before going to start, I hope everybody is awake. Even I'm feeling dizzy after lunch. So hope you won't mind if I am not doing on the, as per your standards. So today I'm going to talk more about what happened in the fiber world, especially the way the technology has changed a lot, especially on transmission side, and what has been the learning and what are the opportunity and challenges ahead as well. So I think most of you would be aware about who we are. So before I take much time, we are one of the largest optical fiber manufacturer from India. And we make optical fiber, different kind of cable, specialty cable, and also make optical interconnects, which is needed for passive connectivity solutions. And we produce more than 50 million kilometer fiber a year. And nearly, around 80% of those fibers we convert into the cable form, and we sell more than 120 countries globally. So we have a very large market, global market actually with us. And all our factories are following the Industry 4.0 standards. So this smart manufacturing technology and process has been introduced. We have 4 innovation center. I belongs to one of the innovation center in Aurangabad, where we are focused mainly on design development, new fiber and its application in telecom and also non-telecom world as well. So I think we have seen in plenary speech today, different generation of technology and evolve. So I will not take much time. You can only recap what has been actually discussed in the morning session, especially how the journey started in 1980s from multi-mode fiber, 1970s actually. If you look at the first fiber was multi-mode fiber, and then slowly it has gone to third generation where 1550, somewhere 1983, where the fiber was used for 1550 band. And after that, you will see like fourth generation fiber was actually being supported for long distance network because of introduction of UDFA available there. And then fifth generation technology has been kicked off in late 2000, I would say 2004 or 5, where DSP has really made a huge difference there. So I categorize actually entire fiber development into 5 parts. So L1 means like maybe you can say level 1, or I put like a very special privilege to say about L5. Actually, in my domain, like these are the 5 L's we see, especially lower values. If you look at the first one, start with the lower attenuation. You see the most focus has been always reducing energy consumption. So it means like repeater spacing can be reduced, and you can go, repeater spacing can be increased with lower loss fiber. So pure silica core has been actually there. I will talk a little more in detail later. And then the second generation has been operational friendly, because the way you are using in the field, if you are bending it, then total internal reflection condition cannot be met under the bend condition. So what happens? Those under the bend condition, you will see the loss would increase dramatically. This can happen when you are installing fiber or maintaining it, or there is a cut where people are repairing in joint closure, or you are not following the best practices. So, to ensure like the operational friendly, solution is there, then trench design has come up, and then we see bend insensitive fiber series has been developed there. After that, people has been looking at the form factor. We basically like how many fibers you could pack in a very small area. So lower diameter was driving force. So from 250 micron coating, it has started to 200 micron first, and then 180 microns already commercially available today. If you want to go further, then we have to also play a little bit glass. Without touching the glass, you can't get there. So we will also talk some of the results what we have achieved, especially with the 80 micron clad kind of fiber what we have developed. And then comes the next generation where you look at somewhere you have heard about 800G, where you require a really large OSNR. And to support that, you have to also look some passive infrastructure, especially in fiber, what is there. So lower attenuation is the one of the things which by default we have to provide to give you better OSNR properties there. And also non-linearity. So lower non-linearity is the key, because to get higher OSNR, you may be also increasing the signal power. So if you increase signal power, then non-linearity threshold will reach very quickly. So to compensate that, we require a fiber which should support larger effective area, so that your non-linearity tolerance become better. And then the last one is about how you are going to increase further capacity in the network, because all L4s, if you look at in single core, single mode, how much we can actually go. But beyond that, there is a limit. Like either you can go L band, or you can look at more number of cores or more number of modes,
So I will touch upon about what are the development happening around the globe and what we are doing actually in that area. So first, let's look at attenuation side itself. So if you see up to somewhere like 1980s, people had developed actually the fiber up to 0.2 dB per kilometer. But after that, it has taken more than 30 years to go from 0.15 to 0.142 dB. So this is a very, very sophisticated processes. So it's not easy to get actually fiber attenuation very low, even though all the manufacturing technology has been perfected. So you can see this is a very challenging problem to handle. And it consists of material science, where you have to look at like totally new material and new processes, as well as on waveguide engineering, because if you just try to look at the lowering the attenuation, then your refractiveness profile changes, then your dispersion profile, everything goes untossed. So waveguide engineering is very, very important to get actually intact. And then of course, precision manufacturing is the key, like where we have to look at. So it's a very comprehensive approach we have to get actually the fiber attenuation getting lower. So otherwise it would have been much easier to get, it would have taken 30 years to get actually 0.01 dB actually attenuation reduction there. Then comes on the bend reduction. So, like when you are seeing any standard fiber, if you try to bend it, the total internal reflection condition is only met when it is straight. When you try to bend it, so under the bend condition, I can't show it here. So under the bend conditions, it doesn't meet the condition of total internal reflection. So light leaks out actually from that. And you could see like one of the depiction about the fiber joint closure, where you would see people would be laying or installing or splicing your fiber there. And there is a proper pathways to actually route the fiber in a larger diameter, but accidentally people can make a very low bend diameter, which you can't rule out. In reality, it happens actually. We have seen at the joint closure, people could go, the losses can go up to 2 dB, 3 dB easily. And when you use different wavelength, OTDR, only then you could see it. Otherwise, you will see as just a loss in the link itself. Then what we have done, we have modified our refractiveness profile, and now we introduce the trend. So you could see G657A2 series profiles we have developed, and the modal field diameter is slightly lower than what typically D fiber has. D fiber was around 9.1, but you could see on the bend loss performance, it has gone more than 40 times actually lower when you compare to the standard D fiber. And our spec has been one of the best specs in the world, especially for the G657A2 category fiber. Then what we have looked at, since in the real field, you don't need to mess up or managing your inventory, whether D fiber, you have to have a separate inventory and A2 is separate. So can we make a convergence of both technologies together and make one fiber where you can actually match those conditions? So we did a lot of research optimization. At the end, we found like even with the trench, we can match actually the modal field diameter in A2. So we introduced a new fiber called Stellar, where you not only have bend insensitivity, plus also we have the modal field diameter match there. Then next migration has been in reduced diameter fiber. So especially started with the coating. So first generation started from 250 to 200 micron, just reducing the coating, always give you more compact dimension, especially putting more fiber in the cable. And but there is a limit, like you can go up to 180 micron easily, but after that there would be a challenge, especially micro bending issues would be actually dominant there. So we have been exploring what is the other possibilities where we can actually reduce the diameter of fiber. So we see, okay, let's explore the possibility of reducing the clad dia itself, because this kind of dimension has been designed in 1980s And since the manufacturing process has improved dramatically, so hopefully we should able to get the desired performance even with 80 micron as well. So we have done different kind of diameter, like 80, 90, 100, 110, all kind of different kind of glass diameter we have looked at. And we found like 80 micron is coming very good. So, and overall diameter has been 165 micron, including the coating. The things is during this process, what we have understood, like there were a lot of challenges, especially on micro bending as well as mechanical environmental reliability issues, because fiber would be more actually prone to this kind of temperature cycling test is had to go through, or different kind of strip force. It has to be there. Ultimately, if you are introducing a new fiber, it has to match the old legacy characteristic very precisely. However, there is a green factor in this, like when you use less material, of course, you are using less energy to produce, and by default, you have lesser wastage, and this gives you more sustainability to the ecology as well. So here I'm showing you some of the latest results, what we have got on our 80 micron clad with 20 terabit, like 200 gig 80 channel, 256 gigabit 80 channel, we have done testing. And we have compared the performance of A2, because this was A2 design, bend insensitive trench design with 80 micron. Without trench, it was very challenging because, as you know, the macro bending was a huge challenge there. So you could see in the table, like most of the characteristic of A2 version of 125 micron glass versus 80 micron is given. They are very similar. The one challenge we are facing, especially on larger diameter fiber, our 80 micron is slightly behaving other way around, like it is giving more losses comparison to the lower diameter. So we are still optimizing the waveguide, and also from academic institution, they may look into that, like what could go wrong and what could be the reason for this kind of interesting phenomena happening. So maybe we can solve this much quicker. However, if you look at transmission performance result, like whatever we had a performance in A2 fiber, which has nearly a dB penalty comparison to D fiber, it matches actually just a standard G657A2 category. So this perfectly is suitable for access network, or wherever you see the bend insensitivity would be critical in operation where we can use it. Then fourth category is coming on low non-ERT. I think I have touched already upon, but you have to look at like G654E is the new standards already available for the low loss and large effective area fiber. Typically 110 to 125 micrometer square, that's a typical effective area, where the standard D fiber has typically 80 to 85 micron square. And the attenuation has been somewhere like 0.16 dB per kilometer. But the major challenge would be, can we get EDFA, which can give you plus 3 dBm per channel power for 80 channel or 96 channel altogether? So it's very challenging to get, because even though you have larger effective fiber to support higher launch power, but there should be EDFA to support that, which we are seeing very limited availability of this. So if some of the research organization can solve this and make a commercial grade fiber with dynamic gain adjustment supporting DWDM with high output power would be great, actually. I think then it will go there. Also, the cutoff wavelength, what we found in this standard is somewhere 1460 somewhere. So it means it can only support S band, C band, L band, O and E band, you will be sacrificing. So you may get certain benefit on lower non-linearity and more capacity in SCL band, but you are sacrificing O band and E band. In terrestrial application, you don't want to rule out, because this fiber is also designed for terrestrial as well as submarine application. And mostly terrestrial fiber has been always either G652D fiber or maybe bend insensitive fiber like G657 series fiber. So we are having development, we are evaluating, we are looking all the characteristic in a very precise, and we look at like what kind of value proposition it could bring actually on table. So maybe some of these problems, you guys can also look into that and see whether some of the solution can be brought in on this platform. Then here the prime objective for the talk here about fifth category, which is where you see space division multiplexing is there. And you could see like it started from Furukawa. I think we are lucky to have one of the colleague from Furukawa group. And it's a very delight opportunity to talk about, like in 1979, they developed 7-core fiber with 150 micron clad diameter and with crosstalk somewhere 43 dB. And now you could see even 2021, 38 cores has been also introduced with different kind of interdimension. So, but what you see here, a number of issues could happen, because if in a given glass diameter, if you are putting more cores, then the distance between the cores is going to be lesser if you are putting more cores. And it means like they will be more vulnerable for the interaction and the crosstalk. Some of these issues I will discuss as well as in future. But before we start on those challenges, let me show you like what are the benefit you can get if you are putting in multi-core fiber in network. So for example, instead of 4 fiber, you can use only 1 4. Your significant diameter reduction will happen in the core, which is inversely proportional to the square root of the number of cores what you are going to put. The glass material and coating material is going to dramatically reduce by 1/4. Same way, weight of the cable will also reduce, and this will help you to deploy faster. Even the diameter of the duct and trench, whatever you are putting, actually all will give you a significant total cost ownership for the faster deployment. However, you get 4 times bandwidth and scalability and the future for the infrastructure, but we have been looking whether we can make a ribbon of multi-core. So the challenge is splicing, because for multi-core splicing, you need to rotate fiber to align the core precisely. If you have a ribbon, it means like all splicing machines should have a cantilever for each 12 fiber in a way that it not only horizontally or vertically should align, also should able to rotate it precisely to match it. So currently, this kind of splicing machine doesn't exist. So it's a very interesting research problem where I would invite your participation to find some solution if we can get it quickly there. Now, the things is about the crosstalk, like why you can't keep so many cores together, because the most of the light is confined in the core region, but however, evanescent field goes outside the core. And when you bring 2 cores closer, so evanescent field start interacting, and that's where the crosstalk is happening. It will not happen at one point, it will happen across the length. It's like a distributed coupling is going to be there across the length of the fibers. So crosstalk in multi-core will always increase across the length. If you are having crosstalk measured at 10 kilometer, 15, 20 kilometer would be totally different values as well. So, but however, we don't need to worry about it. We have to just ensure what kind of transmission system we are going to use and what is the tolerance we are going to expect. So some of the research paper has been published by Peter Binge's group, and they claim like if for 16 QAM modulated system, crosstalk should be less than 25 dB. So if that is the case, then at least your penalty is not going to be more than half dB. So we take that as a reference and we look at our design and we optimize our design and make it the 4-core fibers. Similarly, if you look at outer clad thickness, which is from core to outer side of the clad region, this is very critical, because if you keep them smaller, then the micro bending issues is going to be very severe. So we have reduced, we have to optimize this and to ensure that mechanical reliability and failure would be at the minimal level. Now question is, if you have the fiber made, how are you going to use in a network? So the things is, firstly, you need to identify the cores. So core identification is the critical. So we have introduced a marker, which is like a teeny 5th core, so that you can demarcate as one of the core, and then other cores can be relatively sequenced. And then splicing machine also has an automation and alignment algorithms where with the help of the core, it can track and it can splice. So typically, Fujikura has developed FSM 100P plus for splicing any kind of fiber. And this can give us splice time within 3 minutes. and with a splice loss less than 0.2 dB. So this is then come out like how are you going to use in the field. So connector has to be made. So firstly, fan in, fan out. What is the insertion loss? Typically 1 dB we have achieved, and we can place them, and we have made actually entire transmission boxes, which will be also laid in this AOC testbed project. So where is our journey? This is our journey. Like we started from single 4 core without marker, then we also put trench in this, so that more crosstalk issues can be taken care better. And typical OCT is 30 to 35 micron. And if you look at core pitch, somewhere 40 to 42 micron is there. A modal field diameter is somewhere like 8.4 to 9.1, just similar to D fiber. Here we are showing some of the measurement results what we have got, just to give you idea about how we measure the crosstalk. So typically, worst case crosstalk has been 25 dB after 45 kilometer length, and you can see that attenuation has been less than 0.24 dB per kilometer, the worst case attenuation across different cores, and the dispersion values were less than around 15 picosecond. Then we have done 200 gig transmission just first to ensure like whether this fiber we can transmit signal actually and can go through. So 200 G we did testing, and we compare the performance with the standard D fiber, and we found very similar performance. Non-linear characteristic was very similar to our standard D fiber. After that, what we did, we put a DWDM system in one of the core and wanted to see like, okay, 20 terabit in each core we were transmitting, and seeing in 50 kilometers link we have done, and we found like, okay, there is slight variation, but however the variation is not so significant. So you can see like very similar to G652D performance it has matched. Then what we did the last experiment with like all 4 core were having 20 terabit, so going 80 terabit altogether, and there we have seen like, okay, the crosstalk was really making a difference. So you could see the upper 4 characteristic where the BER has gone higher side. This is limited by the crosstalk. However, if you look at the SD effect limit, it's much below than SD effect limit. So 50 kilometer link, it's perfectly fine, no issues. We can guarantee actually the performance in the network. And we can see like, okay, you can use in access metro application very comfortably. So to conclude, you can see like MCF is a very attractive solution which offers huge advantage in having a superior material efficiency. Space form factor is going to be very compact for high fiber count cable, and also provides you future-proof, scalable, multi-times capacity, data transport capacity, which you may be requiring for comprehensive integrated networks where smart city infrastructure, 5G, 6G, future metro access network, all can be integrated on a single fiber network itself. And you have seen already, I have already described the results, and we strongly recommend that these can be suitable for hyperscale data center interconnects as well as metro and access network. However, we need to focus on, which is also one of the key initiative on this, our testbed initiative to develop low cost fan in, fan out, and other key component, what it is required actually to make it successful, operation and solution for our country as well as across the globe. So thank you very much for your attention. I would be happy to take your questions.
Low latency trading, there are some deployments of hollow core fiber. So any insights or any relevance from India perspective? We see for low latency trading, some operator in UK has actually deployed hollow core fiber. So any insights on that?
Yeah, you were talking about the luminosity actually. That is a startup from Southampton Research Group where it has come out. So the thing is, hollow core is still under. Yeah, probably the next speaker is going to talk more. So maybe I will take a question offline then. Okay. Yeah, go ahead, please. So all these 4 cores are single mode fiber.
Multi-mode fibers also in the multi-core fiber?
You can, but the thing is, where is the business? Because you look at the diameter. The core dimension is somewhere 9 micron, and your clad dimension is 125 micron. And when you look at multi-mode, your clad is going to be core is going to be somewhere 50 micron. So if you have to put more core, it means your clad diameter has to increase. So I do not see actually a compact factor would be deterministic there.
And one more question, sir. You have shown dispersion as 14 picosecond per kilometer per nanometer. So is it the cumulative dispersion? It is the sum of all the cores, or it is for the individual core?
So it is worst case. What we have shown here is the worst case. Like it's less than 15 picosecond per nanometer per kilometer. So this is the worst case dispersion you can get
For the single core?
Yes.
Thank you, sir.
No, all 4 cores. If you look at all 4 cores, the worst case you can get the higher than only up to this values. All other cores will be low, slightly lower than that, in the same range, I would say.
Thank you. We'd like to thank Dr. Mishra for
Thank you.
Very nice session. We now move on to the second presentation. Just want to confirm that Dr. Yongming Jung is online.
Yeah, I'm here.
Yes. Okay. It's my pleasure to introduce our next speaker, Dr. Yongming Jung. He is a principal research fellow at the Optoelectronics Research Center, ORC, at the University of Southampton in UK. And he specializes in multi-core and multi-mode optical fibers and in optical fiber amplifiers. We'd like to mention a few of the highlights that he has been involved in. He has led groundbreaking research on space division multiplexing and on hollow core fiber technology. He has several notable accomplishments to his credit. I'd like to mention a few of them. He has demonstrated the world's first multimode erbium doped fiber amplifier. He holds the Guinness World Record for the multimode transmission, and also has won the European Union's Horizon Prize for breaking the optical transmission barrier. He has successfully commercialized multimode and multi-core fiber amplifiers. He's the originator of 2 large and strategic projects, the European Union FP7 Mode Gap Project and the European Union Horizon 2020 Safari Project. He has published over 380 scientific papers, has a H-index of 48. He has published 3 book chapters, holds 6 patents, and is very active in terms of the research community. So we are indeed honored to have Dr. Yongming Jung with us as a speaker. Over to you, Dr. Jung.
Thank you. Give me a second. It's my great pleasure to give a presentation today. So thank you for your kind introduction. So yeah, actually I'm mainly working on pure fiber, multi-core fiber-based space division multiplexing, but recently I'm also started working on the hollow core fiber. So today I would like to introduce some of the hollow core fiber related technology. So today the title of this talk is the advancement in hollow core fiber component and direct laser interconnection. So let me introduce one of the UK projects. So it is the AirGuide Photonics project. So it is a UK project, and the project goal is translate hollow core fiber technology from the laboratory to the deployable fiber technology. So yeah, so in this work, one of the work package is to develop low-loss hollow core fiber and not only for the telecom wavelength. Give me a second. I can hear some echo. Is okay? Okay. So yeah, one of the activities is to make the low loss helical fiber, and another one is the interconnection with the normal solid core fiber with the helical fiber. And so the activity is to develop the amplifier, fiber amplifier and laser technology, because the helical fiber can provide really wideband transmission. So we would like to develop the new amplifier and laser and trying to demonstrate the wideband transmission and beam delivery. And post activity is the data transmission. So using the helical fiber, it expects the low latency transmission and also ultra wideband transmission. So we are focusing on these two transmission regime. And fifth work is the laser beam delivery. So using the really high power laser delivery or high peak power delivery using the helical fiber. And final application area is the sensor area and metrology. So using the gas sensor or something like that. Yeah. So helical fiber, as you know, light is guiding inside hollow core rather than solid core. So refractive index of the optical fiber is close to 1. So normal solid fiber has a refractive index of the 1.45. So actually helical fiber is about 30 to 40% is light more faster. So it can provide a low latency transmission. And also due to the helical fiber transmission, it has the low linearity due to the air and high laser damage threshold and low Rayleigh scattering and good thermal and radiation stability. Also, helical fiber is the really ideal platform for the gas delivery and gas interaction or liquid interaction as well. More importantly, helical fiber can be flexibly designed and it can provide the wideband transmission. So it can deliver the telecom wavelengths, but it can very good for the UV transmission as well or mid-IR wavelength transmission as well. So maybe I'll try to introduce very recent state-of-art fiber using the helical fiber. So in this graph, red line is the Corning SF20A, and optical fiber loss is about 0.2 dB per kilometer at C-band wavelengths. But in our helical fiber, we call it D-LAN. So it has a multiple thin layer of the cane, and it provides the current loss is very close to 0.174 dB per kilometer. So this helical fiber is lower loss than normal Corning SF20A. So in this structure, there is thin membrane of the glass membrane. So if we employing another layer, typically fiber propagation loss will be about 1 order of magnitude can be lower. So that's why we are very keen to develop this kind of a little bit complicated, but it can provide a really low loss. So in this fiber, it's not only 2-link, it is actually 3-link structure. So it can provide a 0.17 dB loss at this moment. This fiber is even improved now. So it is the fabrication perspective, they improved all the process, and now fiber loss is even less than 0.14. So as you know, silica fiber, pure silica fiber is using for the submarine transmission. So typically this yellow line is core is a pure silica and cladding chlorine doped cladding. So fiber loss typically 0.1424. It is the record solid fiber loss, and our helical fiber even lower loss than this fiber. So, and we can observe some of the small interference effect, but this one is basically from the helical fiber. Long distance is a very good single mode transmission, but if we're using the relatively short length of fiber, still high order mode is existing yet. So when we cut back a relatively short length of the cutback, we are observing that kind of the interference. But when we using it longer length of the fiber. This fiber is really single mode, and fiber loss is currently less than 0.14. And not only the C-band, so if we are focused on the visible wavelengths, so fiber design will be a little bit more smaller dimension, and then we can, the transmission window will shift to the visible wavelength. So especially in 1060 nanometer, the red line, so fiber loss is about 0.3 dB per kilometer and 1060 nanometer. So this loss is much lower than silica fiber. Silica fiber typically 0.8 dB per kilometer. And also at 850 nanometer, our helical fiber loss is about 0.6 dB per kilometer, but solid fiber typically about 2 dB per kilometer. So visible wavelength, this fiber is much better, improve the loss performance. So this one is the more bigger picture of the fiber loss spectrum. So 1550 helical fiber break the record solid fiber loss, and but also visible wavelengths, even lower attenuation, and also UV wavelengths, also low loss transmission. More importantly, in the mid-IR wavelengths, a silica fiber is typically beyond 2.2 micron. Silica fiber does not guide the light. So about beyond the 2.2 micron, silica fiber does not guide the light, even though 1 meter length of fiber loss is very huge. But helical fiber can providing about 10 dB per kilometer scale of the fiber loss. So that meaning is about 0.2 dB per meter. So very state-of-art, very decent helical fiber is available, but so we would like to using it many different application area, but one of the issue is the interconnection problem. So how to interconnect conventional solid fiber with helical fiber. Yeah, plus the issue is the fiber splicing. So simply single mode fiber, helical fiber, with splicing it, we expecting the 4% friendly reflection from the glass and air interface. And also many times there's some microstructure that will be collapsed. And another issue is the mode field diameter mismatch. Single mode fiber is about 10 micron. Helical fiber typically mode field diameter is much larger, so it is more than 20 micron. And helical fiber, as I mentioned, high order mode is existing it, so modal excitation is one of the issue. And to reduce the friendly reflection, one of the research group demonstrating the angle cleaved fiber splicing, but in this way, typically there is some increased fiber loss is happening, and also it can easily excite high order mode, so it is not a perfect way. So in our approach, we introduced microcollimate approach. So microcollimate platform is used for the various fiber optic component fabrication. So commercially, most of the fiber isolators, circulators, gain plate filters, beam splitters are based on this technique. So using this platform, we place the input single mode fiber and then putting the micro lens, and then we can effectively collimate the light, and then using another micro lens, we can focus the light into the helical fiber. So here, very good thing is single mode fiber, solid fiber, we can angle cleave or angle polished, and then easily we can eliminate the panel reflection. So here's one of the example of the fiber. We simply use the photonic bandgap fiber because this fiber supporting more number of modes compared with the anti-resonant fiber. So we're using about 350 meter length of the fiber. And at the beginning, we're just trying to center-to-center splicing. So as you can see, most of the light is in the fundamental mode in the time of flight measurements. So basically, we launch the picosecond pulse laser into the helical fiber and trying to monitor it in the time domain. But we observing the high order mode as well, LP02 mode. So it is the symmetric high order mode. And we trying to intentionally offset launching it, and then we can excite a symmetric high order mode, LP1 on and LP2 on, something like that. So clearly we can see that a number of the spatial mode is
still guided in this fiber, halogen fiber, but by central launching it, we can excite the central symmetric mode, LP01, LP02, LP03, if there is. So that will be happening in this kind of the microcoulometer as well. If input fiber is simply single mode fiber, and probably it will excite the LP01 and LP02, LP03, something like that. So that's why we employing the large mode area fiber. This fiber mode field diameter is well matched with halogen fiber of the MFD. So in this way, so because we are using the same coulometer length, so MFD should be the same, and then it will be the best performance. So to reducing the splice loss between the single mode fiber, we employing the mode field adapter to reduce the splice loss, and also it will providing the better modal excitation. So that is our fabricated device. The total insertion loss is 0.53 dB. So basically, insertion loss from the modal adapter, this region, is from the 0.28 dB, and insertion loss from the microcoulometer assembly is about 0.25 dB. And then high order modal content in the time of flight measurement, so high order modal content is less than 20 dB, and final back reflection is almost negligible. It is minus 50 dB around. So this is the fabricated device. So the beauty of this kind of component is there's some free space is existing it, and we can adding any component inside. So if we putting the isolated core material, and then it is halogen fiber isolator. If we putting the bandpass filter, it will be the halogen fiber bandpass filter, something like that. So many different type of halogen fiber component is possible using this microcoulometer technology. Also, using this technology, we can make the multi-port device. So this one is the 3-port device. So this one is the dual hole feather. So we can plug in 2 halogen fiber. And then if we launch the light from the top fiber, and then 50% of the light will be transmitted, but another 50% will be reflecting it, and then we can collect into port 2 fiber. So in this way, we can make the 3-port device. This one can be beam splitter or WDM coupler. Yeah. So this one is the example of the fiber, and this time we are observing slightly more larger insertion loss, but I just would like to mention it. Yeah, we can make the multiple port device, and also if we using the dichrometer, and then we can realize the simple L band beam splitter using this technique. So yeah. Another topic I would like to mention today is the direct laser interconnection with halogen fiber. Most of laser diode has silica fiber pigtail, but we started considering whether we can directly connecting the halogen fiber from the laser diode, whether it will be interesting. Actually, it is very interesting because if these days lots of people using the quantum cascade laser, so mid-IR QCL laser, and then solid fiber beyond 2.2 micron, silica fiber does not guide the light. So directly we launching the halogen fiber from the mid-IR wavelengths, it will be very interesting, right? Most of people using the soft glass fiber, but soft glass fiber is really easy to break. So even though you just pick up the fiber, it can break the fiber. So it's difficult to clip, and it's difficult to splice. So there's many technical issues. So if using the halogen fiber, it's much more stable. So that's why it is very interesting to investigating direct laser interconnection. Another application is the UV wavelengths. UV wavelengths, solarization and photonic darkening effect is one of the issues. The meaning is today, fiber transmission is 100%, but tomorrow it will be 80%, the next day 60%. The power gradually it will be degraded over the time. So solarization is one of the issue in the UV wavelengths. But halogen fiber, there's no silica, so most of light is still guiding in the air. So solarization effect will be much less. So that's why UV wavelengths direct coupling will be very interesting. So that's why we start to investigate this kind of research. And at the beginning, we're starting with 850 because it's much easier, and using the backside because the backside beam is really circular. So that's why we're choosing as a first experiment. At the beginning, we're trying to use the two lens system. So one lens trying to collimate and another lens trying to focus the light. But here, very important thing is the multiple diameter mismatch, because the waveguide demands typically about 1 micron, hollow core fiber MFT typically about 20 micron. So there is huge difference between two MFT. So in our experiment, we're trying to using the short focal length of the L1, so about 3 millimeter, and trying to change the focal length of the L2. So black line is a simulation, and we noticed that about 25 millimeter, it can best the coupling efficiency, right? So experimentally, red line is our experimental data, so it is quite well matched together, and we experimentally are observing extremely high coupling efficiency, about 95% coupling efficiency into the hollow core fiber. And we also trying to make this prototype of the device. So this one is the backside package, and this side is the hollow core fiber and micro lens, trying to make the collimator and trying to package it together, something like that. So we are working on to make some package, the portable package device as well. So we confirm that 850 nanometer, it can achieve the very high coupling efficiency. Now we start to move to the UV wavelength. So this time we use the laser diode, so 405 nanometer. And we noticed that beam elasticity is quite high, it's 2.5, so it is quite elliptic. And then we choosing the different lens choice, and finally we managed to achieve about 60% of the coupling efficiency. That is good, but yeah, not 95%, but it is mainly due to the beam elasticity. So we're trying to improve the beam elasticity by employing some cylindrical lens pair and trying to make the circularized beam and trying to couple the light. So that is still ongoing research activity here. And second thing is that we're trying to extend our approach to the mid-IR wavelength as well. So we employ the 3.3 micron laser diode and trying to employ 2 different focal lengths. And at this time also we are achieving about the 70% of the coupling efficiency. So that is also very, very nice achievement. And here we think one of the interesting approach is just simply directly butt coupling. So there's laser diode here and hollow core fiber direct coupling. But we expecting that large MFT mismatch. It is 1 micron. This one is about 20 microns. So that's huge mismatch. And so we try it, and it's showing about 10% of the coupling efficiency due to the significant multiple diameter mismatch between the waveguide and hollow core fiber. So this graph, we're trying to pull out the fiber from the longitudinal direction. So that is the spectrum. And then this fiber we're scanning in the X and Y, and then we can make the quantum map. So coupling efficiency is low, but it has large tolerance because this fiber MFT is about 20 micron. So to improve the coupling efficiency in butt coupling, we think maybe gradient index fiber lens will be very helpful, because the concept is more the same. Previously we used the 2 lenses, but the distance between the 2 lenses is not important. So that can be combined into one single lens. So actually laser diode, 1 lens and fiber is possible, right? But that lens can be replaced by the gradient index lens, gradient index fiber. So only important thing is this distance, laser diode and lens, that distance, and lens and out fiber, that distance is very important. So we need to control that length. So we did the simulation first. So here's the laser diode. At the beginning, the light beam start to diverging it, and then gradient index fiber will trying to focus the light, and at some point that is very well matched with the multiple diameter of the hollow core fiber, and in simulation is showing about 90% of the coupling efficiency. And then in experimentally, we're trying to make in this device hollow core fiber. So it is coreless silica fiber. So this one is a pure silica fiber without any core. And then this one is the 50 micron gradient index fiber. So in this way, we achieve very close to 69%, very close to 70% using gradient index fiber-based all-fiber MFD converter. So our future plan using this technique is the two-lens system. We plan to incorporate a cylindrical lens pair to improve the beam elasticity, and then it will improve the coupling efficiency. And our final goal is to making this kind of compact package device. So basically, most of the 14 pin butterfly laser diode package is something like that. So laser chip is here, and the several cylindrical lens or something, and isolator and output lens and fiber, something like that. But if we would like to make the hollow core fiber, so replace this fiber with hollow core fiber, but MFT mismatch will be much larger. So dimension, we expect that this dimension will be almost twice size of this dimension, but it will be very compact. And also we keep working on the bud coupling approach. So currently we're showing 850, but we would like to explore the UV or mid-IR, more extreme wavelengths as well. Another important thing is using this technique can be using really high power application as well. So that is our group demonstrating recently kilowatt CW laser delivery over 1 kilometer length of the hollow core fiber. So this is the high power laser. And then using the two different focal lengths, and then we can improve the coupling efficiency. That is really important because let's assume this coupling efficiency is 90%. Then meaning is 10% of the light will be the input side. So 10% meaning is the kilowatts, 10% meaning is 100 watts, right? So 100 watts will heating up at the beginning of the section. So that is the huge problem. So coupling efficiency is very important, high power delivery. So that's why we need to, best choice of the lens is very important. And so this one is a through output efficiency. So at the end of the fiber, after 1 kilometer length of fiber, coupling efficiency is close to 80%. And fiber loss is this much. So we expecting that input coupling efficiency is about 95% coupling efficiency. So that range of coupling efficiency is very important for the high power delivery. So if we are considering even higher high power delivery, actually we need to consider how to improving further coupling efficiency as well. Yeah. So here's my conclusion of my talk today. So today, microcollimator based hollow core fiber component, and we're trying to make the various hollow core fiber components. So our next plan is trying to make an even complex device using the hollow core fiber and trying to support various hollow core fiber research. Another thing is that we focused on the direct laser diode interconnection with the hollow core fiber, mainly two laser system and bud coupling. So currently we are considering to making the more enhance the coupling efficiency by playing with the beam elasticity, and also with our final goal is to create the compact package the hollow core fiber interconnection. Yeah, that's all. Thank you for your attention today. I couldn't hear you. Yeah.
Many thanks. So if you could share more light on how much lower latency can be achieved with this. We understand normal fiber has 5 microseconds per kilometer. So with hollow core fiber, how much would be the latency reduction? Second question is, we have heard that it is deployed by OFS and Somerset. So what is the status of manufacturing? Are there real deployments? When do you see this to be available commercially for deployment by operators?
Yeah, okay, thank you. So latency perspective, it is about 30% of the latency we can achieve. So yeah, that is simply related with the refractive index of the air and and silica fiber. So latency reduction is about 30%. And helical fiber, yeah, very decent. Helical fiber is demonstrating in our lab, and the luminosity. Recently, Microsoft acquired the luminosity, and they giving a huge effort to improve the fiber loss and cabling. So it's difficult to answer when it's actually a little bit, but big companies start to involving it, and we believe that it will be maybe next 2 or 3 years later, we can see some field deploy over some fiber.
We have one more question, Dr. Jung.
So, Dr. Jung, excellent results. So, congratulations. So, my query is about reliability studies. Have you looked at high temperature, high humidity test of this fiber, and what was its performance, especially on attenuation perspective?
Attenuation perspective, high temperature. I don't know how much high temperature you are considering, but
minus 82 plus 60 degree, and even humidity, you can go up to 30% to maybe 90%, both together.
Yeah. So in terms of the stability, I believe the temperature stability will be not a big issue, because the all material is the silica glass, so it is much robust than germanium doped the silica fiber. So thermal stability. So lots of people trying to make some high sensitivity sensor using the helical fiber, because they're very good thermal low stringency. But one of the issue might be the air inside helical fiber. So there's some water molecule and some gas vapor is inside. So if our application is not resonate with that gas line, it will be fine. But if close to that line, the fiber need to be vacuumized. So it need to make the vacuum, so or applying some inert gas inside the fiber. So that is one of the issues. So people trying to make vacuum the fiber. So vacuum the fiber also very interesting topic. So people working on it, and in that sense, typically vacuuming, it takes some time, and trying to sealing the end of the fiber, and some application need to reopen again. So that is some of the issue, but people are working on it.
Dr. Jung, thank you very much. On behalf of the organizers, we'd like to express our thanks to you for the excellent talk that you have given. The organizers have a memento to give you, but they will send it to you by courier, and it will reach you in a few days. So thanks again for joining us.
Thank you very much. It's my pleasure.
We have come to the third and final presentation of our session. This will be a video recording. This is by Professor Christian Antonelli, who is currently an associate professor of electromagnetic fields in the Department of Physical and Chemical Sciences at the University of L'Aquila in Italy. He leads the laboratory on optics and photonics. He is a member of a large initiative of the city called Innovating City Planning Through Information and Communication Technologies, INCIPICT. This project has got two interesting components. It is an experimental optical network, first of its kind in the world. It is a testbed for validating new and passive optical networking devices and techniques, including 10G EPON and optical CDMA and many such technologies. It is also a metropolitan area network that connects the important sites of L'Aquila city. So he is part of the project and is leading several initiatives. One of the interesting projects of this initiative is that they are using signal polarization in undersea fiber optic cables to locate earthquakes. And again, this is part of the project that he's involved in. His current research explores propagation effects and novel transmission schemes in fiber optic communications and quantum communications. He is a fellow of the Optical Society of America, also known as Optica, and is a topical editor for Optics Letters. He's unable to be with us, but has sent a video recording, which we will play at this time. So over, please go ahead.
Hello everyone, my name is Cristian Antonelli and I'm an associate professor at in Italy. So first of all, I would like to thank Professor Venkitesh for inviting me to present our testbed for space division and multiplexing that we deployed in L'Aquila. Unfortunately, today I was not able to join the workshop in person, but I hope that there will be more opportunities in the future. This is a list of friends and colleagues that helped out tremendously in our adventure, and I would like to start by acknowledging all of them, and I hope that this list keeps growing with time. In L'Aquila, we're interested in space division and multiplexing in optical fibers, and I'm sure that there's no need for an introduction on the subject in this workshop. The reason why I'm showing this figure that I took from a mini review that was recently published in Optica by Ben Putnam, Georg Rademacher, and Ruben Lewis is because it clearly indicates that SDM provides an effective way to keep scaling the capacity of fiber optic systems. The starting point of SDM was probably the plenary talk of Andy Kraft-Levy at ECOC 2009, where he came up with this slogan of the coming capacity crunch of the global fiber optic network. That is when we all started working on various aspects of space division multiplexing in optical fibers. And since then, the question of whether and when SDM will become a reality has been actively debated. This is a list of controversial workshops that took place at OFC since 2011, and this list keeps growing. In L'Aquila, we thought that we had a unique opportunity to contribute to this debate by deploying for the first time on Earth a testbed for space division multiplexing that could be of use for the international community that is working on SDM. The starting point of our story is the earthquake that on April 6, 2009 pretty much destroyed the city center and caused more than 300 casualties. The city of L'Aquila, as you can see in this figure, is in the center of Italy, close to the Adriatic coast. After the earthquake, the Italian government funded Project Incipit. This is a big project whose mission is to conceive the city as a living testbed for a number of integrated ICT applications in the framework of smart city paradigm. At that point, it was clear that we were in a special situation because the tragedy of the earthquake transformed L'Aquila in a special place where it was possible to do things that is much more difficult to do in any other place. And this includes deploying special fibers like fibers for space division and multiplexing. So then we started planning and deploying our infrastructure, which consists of two rings. The first ring is approximately 7 kilometers long, and it is hosted in a special infrastructure, which is a walkable underground tunnel that runs underneath the city center. The tunnel hosts a number of services, including water, gas, electricity, telecom, and we were given permission to deploy our SDM fiber cables in the top right track in the tunnel. Here we deployed multi-core fibers which were provided to us by Sumitomo, and a few more fibers which were provided to us by Prysmian. The second ring is 20 kilometers long, and it is in the process of being deployed, and it consists of regular ducts, which are only a few tens of centimeters underground. The Laboratory of Optics and Photonics gives access to the fibers, and it is located in the heart of the city, in the Rectorate building. These are pictures of the lab as it looks nowadays. On the left, you can see the entrance of the Rectorate building, which is a magnificent ancient building which was fully renovated after the earthquake, and now hosts also our lab. And this is a picture of the lab during an experiment that was performed recently, a few months ago. Our SDM fiber cables, as I mentioned, are deployed on a rack on the top right side of the tunnel. Both the multi-core fiber cable and the few-mode fiber cable are loose tubes, and they contain a number of fibers. They're filled with some jelly material, and they have strength members inside. In addition to the multi-core fiber cable and the few-mode fiber cable, there's also a cable with 24 standard single-mode fibers, which are typically used as a reference. The multi-core fiber link has been fully functional since June 2019, right before the pandemic. And these are pictures that date back to those days, including a picture from the grand opening of the testbed, as well as a picture from a workshop where we celebrated the deployment of the first multi-core fiber cables in the history of optical communications. This is our multi-core fiber asset. It includes 12 strands of coupled core 4-core fibers. These fibers are designed for long-haul transmission in a point-to-point configuration because the cores are strongly coupled with each other, which implies that signals transmitted in the various cores couple strongly during propagation, and they require multiple input and multiple output techniques of the receiver in order to be disentangled and received. And these fibers can work in the C12 bands. Then we have 4 strands of uncoupled core 4-core fibers, which are designed for shorter reach applications like access, and they are designed to work in the O12 bands. Finally, we have 2 strands of uncoupled core 8-core fibers for short reach applications in the O band. Out of the 12 strands of coupled core multi-core fibers, 11 were spliced together so as to form a longer span of approximately 70 kilometers, and this pan can be addressed by means of spliced fan-in, fan-out devices. On the other hand, all the other fiber strands can be accessed independently. They can also be concatenated by means of multi-core connectors that are spliced to them, and they can be addressed by means of connectorized fan-in, fan-out devices. So an important reason to deploy SDM fibers is to verify whether the key propagation characteristics of those fibers remain or change when the fibers are cabled and afterwards deployed. And this is the first lesson that we learned about attenuation. So you can see in these three figures that essentially attenuation didn't change significantly from the stage of fiber spool to that of cable on drum, and finally to that of installed cable. Actually, you can see that there's a little reduction in attenuation from one stage to another, but nothing major. On the other hand, intercore crosstalk, which is a key parameter for uncoupled core multi-core fibers, is seen to change from one stage to another. In particular, in the case of the uncoupled core 4-core fiber, the crosstalk is seen to increase by approximately 5-6 dB from the stage of fiber spool to that of cable on drum, and of approximately 1-2 dB in the case of the uncoupled core 8-core fiber. No significant change is observed from the stage of cable on drum to that of installed cable, and the increase in one strand of uncoupled core 8-core fiber was essentially due to a rotational misalignment in the fiber termination. In the case of the coupled core multi-core fibers, we had a pleasant surprise by discovering that modal dispersion reduces from the stage of fiber spool to that of cable on drum, and finally to that of installed cable. In fact, modal dispersion is a critical propagation effect in SDM systems based on the use of fibers with strong coupling between modes, because it is responsible for setting the complexity of the MIMO DSP receivers of these systems. And the reason for the reduction of modal dispersion seems to be in the fact that the fiber is loosely, but not too loosely bent inside the cable. So we were able to measure a modal dispersion of about 2.5 picoseconds per square root kilometer in one strand of the deployed fibers, and this is still today the record low modal dispersion value ever measured in coupled core multi-core fibers. Another important lesson that we learned is that the tunnel is extremely stable. We learned this during an experiment where we were interested in characterizing the phase drift between the cores of our uncoupled core multi-core fibers prior to deploying a multi-dimensional quantum key distribution protocol. And it turned out that the PLL algorithm that we used took about 3 seconds to stabilize the phase difference between different cores for tens of minutes, essentially. This allowed us to successfully demonstrate a 4-dimensional QKD protocol over approximately 50 kilometers of our deployed multi-core fibers. And we took advantage of this ability to demonstrate for the first time real-time MIMO transmission over a field-deployed coupled core multi-core fiber in this experiment that was presented at OFC 2022. So after we deployed the multi-core fiber cable, we had to wait until the end of the pandemic to finally deploy our few-mode fiber cable, which has been fully functional since July 2022, and these are pictures that date back to those days. Our few-mode fiber is a graded index low differential mode group delay fiber with 9 linearly polarized modes, which means altogether 15 spatial modes. And this poses the legitimate question of whether we should still call this fiber a few-mode fiber or more properly a multi-mode fiber. At any rate, the few-mode fiber cable is 6.1 kilometers long. Initially, the 8 fibers in the cable were spliced together so as to form a longer link of 48.8 kilometers, and the fibers can be addressed by means of a max-dmax pair based on multiplane light conversion technology. Now, since splicing fibers of this type is definitely much simpler than splicing multi-core fibers, it is no problem to use a single strand of few-mode fiber in the cable or to splice a few of them to form a span that is of some suitable length. So this was the first experimental characterization of our deployed few-mode fiber, and it included also data transmission up to 48.8 kilometers, demonstrating no noticeable performance degradation after cabling and deployment, and this was presented at ECOC last year. And a broadband characterization of the same fibers based on swept laser technique will be presented at ECOC this year. Okay, so we are now ready for new fibers. As I mentioned, in these very days, we're starting to deploy our second ring of approximately 20 kilometers. This ring consists of regular ducts, which are only a few tens of centimeters under the ground. And we will be deploying more multi-core fibers and more few-mode fibers in these ducts. We're very excited about this new infrastructure because these fibers will be much more coupled to the external environment compared to the fibers in the tunnel, and this is a very important property for applications like sensing that is so trending these days. Moreover, we have room for more fibers to deploy, and therefore we are open to fiber manufacturers that are interested in deploying new special fibers. I should stress that deploying fibers is definitely challenging, even in L'Aquila. And probably the biggest challenge is to establish an effective interaction with the municipality and the other public institutions that are involved. This may take time. I must say that we started this process already a few years ago, and only in these days we see that this is happening. So what is that we want to do with this testbed? Well, we want to share it with our community. The testbed is primarily designed for research collaborations on SDM transmission, study of propagation effects, implementation of secure transmission, study of environmental sensing. The testbed is also good for testing SDM technologies of various types, from components to devices, subsystems, and network protocols. And it is also a very good opportunity for project proposals, because the testbed is the right place for demos, for field trials, and for the implementation of a number of use cases. So it is very important to keep in mind the existence of this testbed for purposes of this type. In the framework of research collaborations, there is no fee to pay to use our testbed. Actually, we are willing to share all we have in our lab. What we ask is that you send over what we don't have, come to L'Aquila and do experiments with us. And to facilitate this process, we prepared a detailed lab inventory that, of course, we're willing to share for this purpose. As I mentioned, our testbed is a very good opportunity for research proposals. This is a national project on space division and multiplexed transmission, fully based on our infrastructure. And we're especially proud of this project because all groups that are active in optical communications in the Italian academia are participating to this project. And this is a list of projects that have been funded, also based on the testbed, starting in 2019. Some of them ended already, and some are still in progress. I would like to conclude with this slide. If you want to know more about our initiative, you can look at the website of INCIPICT, or you can read the article that we wrote in the IEEE Photonics Society newsletters in April 2020, or you can send me an email, and for sure I will give you the information that you need. So with this, I concluded my presentation. Once again, I'm sorry for not being there in person. Hopefully there will be more opportunities in the future. And again, thank you for inviting me to present our initiative, and thank you for your attention.
We thank Professor Christian for the presentation, and also what seemed like a fantastic offer for research collaboration, technology testing, and for project proposals. Not to be outdone, IIT Madras, along with Sterlite, under the funding of the Advanced Optical Communications Program of the DOT, is going to set up a testbed, something very similar to that. This is a project that involves 3 academic institutions, 6 industry partners with CDOT as the implementing agency. Since we have a couple of minutes, may I request Professor Deepa to tell us a little bit about the exciting opportunities that we will have with a testbed very similar to this, to what Professor Antonelli described right here in the IIT Madras campus. And then I will conclude the session with some closing remarks.
Thanks, David, for giving this opportunity. So what Antonelli described is a testbed which is claimed as a field testbed, which is in a tunnel around the city of L'Aquila. We have been following that activities of that testbed ever since that took off, and usually Sumitomo or the fiber manufacturer goes there with a cable. Then these big laboratories, NTT, NICT, Bell Labs, they go with their equipments and do the experiments. And these are the hero experiments that get published in ECOC, OFC, and so on. And now I say that I recently, last October, I had visited Italy, and we learned that they have a lot of equipments already available now. So people can just go with only what is necessary. There is a inventory that is available, and you pay for that inventory, very nominal cost. And you occupy the lab for a week or 2 weeks, and you run your experiments. That's how it runs. Now, even though the funding for that project over the years have crossed about more than 200 million, right? We are starting with much frugal funding, and we hope to establish not just one test bed, but what we plan to establish under the Advanced Optical Communication test bed funded by DOT is platform which would serve as the go-to place, and for testing not just fiber, but several parts of the infrastructure. So the whole communication system is built of transceivers, several components, amplifiers, fiber, and so on, and the network. So this testbed is coming not just at IIT Madras, IIT Delhi is also a partner in that. So there's one facility in the north of India, one facility in the south of India. Particularly in IIT Madras, we will have a field testbed of multi-core fiber. So unlike the cable that is laid neatly on a rack or a shelf, we will go probably the first time in the world, the real testbed where the fiber will be the fiber cable, the multi-core fiber will be cabled, and it will be ducted, trenched in IIT Madras campus. I will probably talk more about that tomorrow, but there is about 4 kilometers of fiber which is running from IIT Madras gate to the computer science department. That route map is already identified. We are waiting for the last minute confirmation on certain things. That will have, the same cable will have 12 strands of 4-core fiber and 12 strands of single mode fiber, so that there can be a one-to-one comparison between the 4-core fiber and the single mode fiber possible. And not just that, a lot of you would already know that a lot of fiber installation in India is aerial fiber, right, between the posts. And we see a lot of greenfield multi-core fibers deployment use case in antenna to the base station kind of installations. So what we also plan is an aerial testbed. So there'll be a 1 kilometer long aerial testbed with, I think, 150 meters between the posts. So maybe about 8 or 9 posts. And that will also get terminated in the lab. There will be provision for loop back experiments. So with about 4 kilometer with 12 fibers, you can multiply and find out what is the total length we can test. Similarly for 1 kilometer as well. In addition, there will be about 10 kilometer of fiber available in the lab for any other tests. It will be like a non-cabled fiber, just a bare fiber, probably spooled with fan in, fan out. And the fan in, fan out by itself is a critical technology. So another work package in the testbed is actually developing that as an indigenous product. So over the next year, there will be a fan in, fan out being developed. The transceivers that would go with these in the deployment use case is also getting developed as another work package. And one last thing is about transmission of analog signals through this testbed, because in going forward in 5G and 6G in the morning, we talked about a lot about convergence of optical and wireless systems. So this testbed will also have provision to transmit analog signals, quantum key signals through one of the cores through this field testbed. So we will keep publicizing as and when our testbed is ready. We hope in 8 months' time, this testbed starting from now, 8 months' time is where our timeline is. Thanks to Sterlite Technologies who are partnering with us on this. We have done the first initial testing of the fiber in Sterlite already. Now they have to cable it and we will have to do the deployment. 8 months is the time scale. And we welcome you all to not just visit the testbed, but be a user and let us know how we can help solve technological problems associated with anything in optical fiber communication technology. Thank you.
Thank you, Professor Deepa. And to bring this session to a close, just wanted to sort of recap the key takeaways from each of the three presentations. Dr. Arvind Mishra, he talked to us about state-of-the-art multi-core fibers, some of the advantages and some of the research challenges that are open before us. Dr. Yongming Jung, he talked about the state-of-the-art of hollow core fibers, various aspects of splicing and interconnection, and the performances that we can get. And Dr. Christian Antonelli talked about space division multiplexing and about the test bed and various applications that we can drive from there. If you have any questions for Dr. Antonelli, please send an email. The email ID is AOC, Advanced Optical Communications, AOC IITM, one word, aoc.iitm@ee.iitm.ac.in. We will collect the questions, send it to Dr. Antonelli, get the answers back, and then get it back to you. If you have any questions for Dr. Yongming Jun also, please do the same. So with that, I'd like to thank you all for attending this session. Hope there are a lot of takeaways from that. Dr. Mishra is here if you want to catch him for some questions over coffee. Thank you very much.
Thank you, sir. Now I request Dr. Sudeshra Srinivasan to please come to the stage for honoring our sessions. Thank you. So it's time for a tea break. We have made arrangements for the same just outside the hall where you had the lunch. And please feel free to visit the exhibition if you have not done yet. And we'll be back by 4:55. Thank you.
Hello. Good afternoon, everyone.
Hi, Dr. Novak, can you hear us?
Yes, I can. I apologize.
No worries. We're just getting started now. Okay. So let's get started, everyone. So we are here for the session. So this is on 5G and 6G microphotonics for 5G and 6G applications, and we have two invited speakers with us. My name is Amol Chaudhary. I'm a faculty at the Indian Institute of Technology in Delhi and the Department of Electrical Engineering. And I'm part of the Advanced Optical Communications Testbed that Professor Venkatesh mentioned. So I'll be chairing this session. So the first speaker we have is Dr. Dalma Novak. So if you work in microwave photonics, you would know that she needs no introduction. You've obviously read her fantastic review paper with Jose on microwave photonics combines both worlds. I have read it many times, and of course, it's a great paper. So if you haven't read it, I recommend reading it. It's pretty well written. Dr. Dalma Novak is a VP of Engineering at Octane Wireless, where she develops high-performance RF over fiber technologies for commercial and defense wireless applications. She's also an honorary professorial fellow in the Department of Electrical and Electronic Engineering at the University of Melbourne in Australia. And she has more than 30 years of experience working in optical and wireless communication field. She's written several book chapters, more than 300 publications in fiber wireless communications and radio fiber systems, and has extensive technical leadership and project management experience in industry as well as academic sector. She co-founded Faraday in 2004 and spent 12 years at Uni Melbourne. She's an IEEE fellow, and in 2018 she received the IEEE Photonic Society Engineering Achievement Award. So it is my immense pleasure to give the floor now to Dalma. Please go ahead. Thank you so much.
Thank you very much, and good afternoon, everyone. And thank you so much for inviting me to talk at this workshop. I'm delighted to be here. Let me just share my screen. Can everyone see my screen? If you can't, just let me know. I think I can see myself there, so that's good. So I wanted to talk today about radio over fiber technologies for 5G, but also for future 5G networks. And so I wanted to cover a number of topics. The first is sort of I think most of you probably know, if you work in the field, why fiber is used to transport radio signals. But I wanted to quickly introduce that before talking about how 5G is transitioning to 6G and what some of the opportunities are for analog RF over fiber links in future 6G networks that work in the millimeter wave frequency range. So just to give a perspective, when we think of radio signals, we're thinking about anything that works in the hundreds of megahertz frequency range up into the low terahertz range. And within that very, very wide spectrum application, there's all different types of frequencies being allocated for different applications. And obviously, the spectrum allocation is different all around the world. And so I just show an example of the US one here. But this sort of area here is really all about wireless communications. And as time has gone on, those frequencies have evolved as well. So, you know, very early on, as soon as fiber optic technology was invented for transmitting digital signals, it was immediately used for transmitting RF signals because it has low attenuation loss. But the other key advantage of optical fiber is the fact that the loss does not depend on the actual frequency of the RF frequency. Compared to coax, for example, when you look at coax, if you have a kilometer of coax and you want to put a 2 gigahertz signal over it, then the loss is hundreds of dB. Unlike putting a 2 gigahertz RF signal over optical fiber, where the attenuation is still just half a dB. So that's a really big advantage. But then you also have the other aspects of fiber, the fact that you can't access the signal, so it's isolated, you get resistance to electromagnetic interference, and it gives you a lot of design flexibility as well. And so very early implementations of fiber radio systems, which sort of evolved about 3 decades ago when digital telephony was sort of first introduced, they were based very much on having an analog optical link, taking that RF signal, putting it onto an optical carrier and doing a direct detection scheme at the other end. Over time, once those wireless networks evolved to cellular systems, we've really seen the evolution to digital fiber optic links. That's really where we are now. And so these types of digital fiber optic links support a number of different applications, whether it's for in-building, outdoor, backhaul, fronthaul is a really big application space for these types of systems, and also fixed and mobile wireless access as well. So I wanted to cover a little bit about 5G networks to sort of give some perspective of where they're going, particularly in terms of the data rates that need to be supported and also the carrier frequencies themselves. So, you know, we started off 4 decades ago with 1G systems. This was just all about analog. This is voice only, and these were analog systems. Then the data got into the digital domain. We started to see increases in data into the kilobits per second. And then over time, we added not just voice, but we added data and also video. And, you know, clearly we know data and video are real drivers for that high data rate that we need to support right now in our networks. So we went to megabits per second of data. And then over time, we went to 3G, 4G, and now we're having 5G deployments for a number of years now. So 5G is all about going anywhere from 100 megabits per second up to 10 gigabits per second to the user. And there are a number of different use cases. It's about increasing the connection density. So one of the applications is this massive machine interconnection communications, where you have a very large number of, that's almost like a massive Internet of Things, very large number of users, each only using a little bit of data, for example. Other applications that require very reliable signals with reduced latency, so being able to get your data immediately with no time delay, these ultra reliable low latency communications. And then also enhanced mobile broadband, where we want more data to the user. We want to increase the availability of that network, but we also want to reduce the network usage as well. So these are some of the key application spaces for 5G. So when you look at those diversity of services that I just mentioned for 5G, not just the diversity of services, but there's also diversity of the spectrum. So as the research in 5G evolved, and you can see the timeline here on the bottom, going from about 8 years ago, you started to look at, first of all, increasing the data rate. And the way that the data rate was increased was to go up into the millimeter wave frequency spectrum, where you were able to get more bandwidth to support that high data. So the early research experiments were very much about using the millimeter wave spectrum, but they were very much about point-to-point links, showing high data rates at millimeter wave frequencies. So that has sort of kind of evolved over time. But then in addition to that, you started to have the development of the standards. And so the standard for this 5G new radio, and then you also started to see deployments. The first deployments were what was called a non-standalone. That means that this type of technology that allowed you to get higher data rates to the user was really leveraging existing 4G networks and building off that technology and that hardware infrastructure that was already in place. Now more and more you're having these 5G network technologies being introduced that are standalone on their own and offering much larger capabilities and also future-proofing too. But the standards are really encompassing and allowing for different frequency bands to be used, both in terms of below 1 gigahertz in the mid-band frequency region, but also in the millimeter wave frequency region as well. So most of the 5G spectrum right now around the world is really focused on that mid-band, particularly in the 3.5 gigahertz spectrum. That's where a lot of this is happening. What you see down here are some examples over the last couple of years. The acronyms here are just referring to different countries around the world and where they have focused on in terms of the frequency bands of their 5G deployments within that country. You can see quite a few in the mid-band, and also there are a handful in the higher frequency range as well. Right now, there's probably only about 10% of the deployments of 5G networks that are actually in the millimeter wave frequency band itself. And there are reasons for that. It's more challenging and it's more expensive. And as I said, initially it was non-standalone, but now it's standalone systems too. At the start of the 5G deployment, it was China and Korea were really leading the way in terms of the penetration and usage. But now there are markets around the world. More than 90 countries around the world have 5G deployments, and there are more in developing countries are continuing to deploy 5G systems as well. So the next thing beyond 5G is called 5G Advanced, and this is sort of seen as a sort of precursor evolution to potential 6G. 5G Advanced is they're working on those standard releases right now. They'll be released in a couple of years' time. This is focused sort of trying to improve the 5G requirements, but very much focusing on the uplink technology to improve the speed for the uplink, the coverage, the mobility, and as well the power efficiency too, for different types of applications, MIMO, and also AI and XR as well. So where they see the 5G advanced standards and requirements is to really sort of be the precursor for studying technologies that could potentially become a 6G standard. So 5G, there have been deployments in the millimeter wave frequency range. Some of these have been just sort of field trials, but some are actually now real deployments. In Europe and in Asia, they've tended to focus on the 26 to 28 gigahertz frequency range. US is also looking at frequency ranges around the 38 to 40 gigahertz. The main application for this is really fixed wireless access for private networks and also rural distribution. So the main benefit being higher frequency, you can get more data, not necessarily to an individual user, but a very high amount of data going to an enterprise, for example. So where is 6G going to go? So there were already companies looking at and starting to think about the technologies and what this might look like. Here's an example of Ericsson. So you can see that the blue bars are showing the current 5G spectrum ranges in the mid-band and also the millimeter wave band. And potentially 6G could be maybe around the 10 gigahertz, but also increasingly people are looking at sub-terahertz frequencies. So anything from about 80 gigahertz and beyond, and in excess of 100 gigahertz. Now, going into the terahertz frequency range obviously is not without technical challenges. First of all, you have a real issue is how that signal propagates through free space. As you take a frequency and you go up in frequency, that signal gets attenuated much more rapidly due to air and water molecules. That's well known. So propagation is going to be something that has to be addressed. If the signal gets propagated and gets attenuated very quickly, that means we're going to need to have more antennas, more repeaters. So the hardware will have to be replicated more frequently. However, you can support these very, very high data rates as you go up to terahertz frequency range. But right now, the componentry that you could really get is very much limited in terms of what's available in terms of RF frequencies. And because of the propagation issue, the coverage area, as I said, is going to be small too. So what I wanted to now talk about is sort of go onto the optical domain to show and talk a little bit about how radio over fiber technologies could potentially support these new emerging 5G advanced and 6G networks that work up into the sub or even terahertz frequency range. So as I said, right now, front haul networks conventionally, if you look at a 4G or even a 5G mobile network, it's about a digital link. So when you look at optical transport in a 4G network, for example, you have two parts of that optical link. The connection between your mobile switching center, between your backbone network and the baseband unit, which is essentially where all the control of the digital bits happens. That happens using a Ethernet fiber optic link, using packets. The connection between this baseband unit and your actual antenna, which has your remote radio head, which has your RF equipment in there, is done through a fiber optic link, a relatively short one, up to about 5 kilometers in length, that is essentially a digitized link. So what happens is at the baseband unit, you've got bits happening here. Those bits actually get converted to an lower intermediate frequency, and then they get digitized. And so it's this digitized signal that gets transported to the remote radio head, where the signals are recovered in the digital domain, and then they're up converted into the required RF frequency. And there are several standards that exist that support this digitization process. These are two of the ones that are well known. So fiber is a well-established technology for the backhaul component of the 5G deployment, as I've shown here, and will continue to be so. Initially, a lot of the backhaul for 5G was being done also through the millimeter wave, very high frequencies, line of sight point-to-point links, and a little bit of free space optics. But fiber has really taken over a lot of the technology space for the backhaul part. So what are some of the challenges with implementing the front haul, that digitization part, for future 5G networks? The key challenge really is what happens when you do the digitization. What I've shown here is some of the functionality of the different elements that exist within your remote radio head and the digitization processes. And the bandwidth associated with this digitized link is proportional to all the different factors that I've shown down here. It's proportional to the sampling rate that you need when you digitize the signal, the number of quantization bits that you need in order to get a particular signal to noise ratio, the number of frequency bands in that wireless network, how many antennas you may have up here. And also there's a little bit of overhead when you to support the required network as well. So I've shown an example that shows that you have an intermediate frequency, say, let's say of 100 megahertz. We've got 5 different channels here, spaced 20 megahertz apart. And the sampling rate that we determine we need is around 30 megasamples per second. And also we need a number of quantization bits in order for our particular system of 30. When you now multiply all these numbers together, you get a bandwidth of 40 gigabits per second. So we suddenly went from a intermediate frequency of 100 megahertz going to 40 gigabits per second. And so recognizing that 100 megahertz intermediate frequency will only be supporting a data rate up to around 20 megabits per second. So we went from having to support a data rate to the user of 20 megabits per second now incurring a digital optical bandwidth of 40 gigabits per second. So you can really see how you're going to have this data bandwidth escalation issue if we're going to 5G and 6G plus networks, where we're talking about data rates to the user of 10 gigabits per second to the user. So this is a challenge, and this is being recognized. There's a new standard called Enhanced CPRI, where they're trying to change some of the partitioning of where these different functionalities take place. But it does lead to some challenges because of you have some trade-offs in terms of the latency that takes place. So this is something that I think will be an ongoing challenge. But really, I think this provides an opportunity for analog RF over fiber links, because fundamentally, this is the simplest type of configuration that you could have to support very high frequency signals with high data rates over optical fiber. Fundamentally, they're not dependent. They don't introduce and escalate the bandwidth. As long as you can get your optical components to support the required data rate, that can be completely transparent to that. The key issue, though, is it's not compatible with time division multiplexing, with conventional baseband systems, and those. So that's really why our analog evolved to digital. But I do think there may be some niche applications where analog RF over fiber could play a role in future 6G very high frequency signals. So when you look at the impairments that you have in a analog RF over fiber link, I'm just showing the example of a signal being received by an antenna, being converted into the optical domain, transported to the other end, going from O to E, and then received. You've got impairments that will determine what signal to noise ratio you can get in that system. The key part is going from the electrical to the optical domain, which instantly gives you a impairment of at least 20 dB once you go from the electrical back to the electrical domain. You've got parameters associated with your photodetector, like shot noise, thermal noise as well. Both of these devices are nonlinear as well. And then you've got the characteristics of the optical fiber too. And dispersion is a real issue. And there was a lot of research done, and there's still research being done, how to reduce the impact of dispersion as you go higher and higher in frequency. And this graph shows why this issue is so much of a problem. You can see that the phase shift when you have a typical optical spectrum in this type of RF over fiber link that uses intensity modulation direct detection, basically these two sidebands are spaced at the RF frequency itself. And so they have a phase change associated with them that increases the higher the RF frequency. And fundamentally, what happens is that you get a power impairment, and you can see that here on the log curve. If you have a 30 gigahertz frequency, for example, you're going to be limited to only about 1 kilometer of fiber transport length before you lose at least a couple of dB of RF power. So that's a big issue. And there are ways that you can overcome this. However, you can use sort of some conventional approaches like using dispersion compensation techniques, fiber Bragg gratings. You can also do some clever things by modifying the optical spectrum itself to only have one sideband, for example, or to actually suppress the carrier itself. That's another way in which you could do this. But in addition to the dispersion issue, there's also the challenge with getting very high linearity for very high frequency links over large bandwidths and also large instantaneous links. And again, there's been a lot of research done on trying to address this, both prior to the signal being put over the optical link itself, looking at pre-distortion, looking at techniques in the optical domain using feed forward or feedback, doing it after you receive the signal in the post domain, down conversion, doing some digital linearization, but also using some clever designs of your optical components. And there's been some reasonable success with that. Here's one example where you could actually do some linearization using digital signal processing. So if you transport it as an RF over fiber system, do some frequency down conversion, but then if you convert it going from analog to the digital domain, you could then use some DSP on the bits to actually improve the linearity. And that allows you to reduce and relax some of your component requirements. So in terms of what type of transport technologies you could use to look at transporting very high frequency signals, not just in the high millimeter wave, but sub-terahertz, this is some work that we've been doing with applied physics labs here in the US. So they developed a technique to be able to essentially generate optically a terahertz signal using a fiber ring resonator. And not only does this signal exist at 100 gigahertz, it's tunable. You can see these are all the RF tones that are generated from 30 up to 100 gigahertz. But they're also very, very low phase noise as well, which gives you very good link performance. And so we use this approach to actually implement a radio over fiber system. We took one of the wavelengths and then we modulated that with some demonstrated gigabits per second of data. And we did some point-to-point links indoors and also outdoors as well. And you can see that when we're going to these very high frequencies, like 60 gigahertz in free space, you do need good amplification in order to overcome that propagation loss through free space, and also high gain radiators as well. And a similar type of approach, this is work done by NTT, where they used a similar concept using a single optical modulator to generate multiple frequency combs. You can then put those combs over optical fiber and then use a direct detection scheme to select off particular wavelengths to give you this terahertz signal over optical fiber transmission system. And so using this approach, they were able to do a link demonstration where they were able to achieve 10 gigabits per second. And not only could you do that, but if you combine this with using some digital signal processing as well, you could also get even higher data rates. So this was also work done at NTT. Sorry, with Nick, you can see that they were able to use DSP to get a data rate in excess of 40 gigabits per second. So this is, again, is some of the technology that you could use in the optical domain to get very, very high data rates, the sort of data rates that 6G is being considered. And so just to summarize, I think that the deployment of these future 6G networks working at very high frequencies offers some real interesting opportunities for analog RF over fiber links to be successfully implemented, and they have a number of benefits over this conventional digitized fiber optic front haul architectures. I think, for those of us who are doing research in this area, and I continue to do this, there are opportunities for new link designs, but also focusing on the devices themselves, high performance, not just optical components, but also RF electronic amplifier technologies as well for these types of systems. So I'll finish there. Thank you for your attention.
Thanks, Dalma, for that excellent talk. So I'll open the floor for questions. Are there any questions for the speaker? Yeah. There's a question there.
Am I audible? Hello. Yeah. I would like to know what are the steps you have taken to increase the SFDR of radio or fiber link?
So we've done a few different things. One of the things, we've done a more straightforward scheme, which actually uses a type of link that is low biased. It's an externally modulated link. And then we bias it off quadrature, which actually allows us to suppress some of the noise and improve the linearity. In addition to that, we've developed a feed-forward type of linearization that actually works in the optical domain by optically effectively getting rid of the optical noise component that is contributing to the intermodulation distortion. And we've been able to get very high SFDR in excess of 120 dB per hertz to the 2/3 using that particular approach.
Thank you. Any other questions? So essentially you've talked about the links. So have you also looked at inserting some sort of functionalities in there to have high performance functionalities, for example, of filtering or in phase shifting or some of these other components as well?
Yeah, we've looked a little bit at that. We've been looking sort of more on the, I guess on the link design. Sorry, on the link design side, not so much on the optical component side, but certainly I know other research groups have been working on those types of techniques.
Thanks. Any other questions? If not, let's thank Dalma again.
Thank you. Thank you very much for your attention and enjoy the rest of the workshop.
Yeah. So thanks for giving this talk. On behalf of the organizers, there's a small memento which will be shipped out to you and reached you in a few days.
That's very kind of you. Thank you. Bye-bye, everybody. Bye, everybody.
I'll introduce the next speaker. So the next speaker is Dr. Meena Dasan. So Dr. Meena obtained her doctoral degree from ISC Bangalore. And she's currently working as a senior scientist at the Electronics and Radar Development Establishment, LRDE in Bangalore, DRDO, and is leading photonics-related development activities. She's the recipient of various awards at lab and national levels, which include the National Technology Award for Development of New Patented Technology, Digital Beamforming Technology for Radars, Agni Award for Excellence in Self-Science, and many others. She's filed multiple patents and has published 80 papers. And she's co-authored a book on field programmable gate arrays and the book chapter on WDM systems. She is a senior and honor society HKN member of IEEE and reviewer for a lot of the reviewing journals. And her research interests include phased array radar systems and microwave photonics. So it's my pleasure to introduce and welcome Dr. Meena.
I'll stand this side, then I'll wait. Okay. Well, a very good evening to all. Let me thank the organizers for giving me an opportunity to be part of this event today and share my thoughts from a different perspective. Since many of these radars which are working in micro domain as well as the millimeter wave domain are using most of the common technology. In this session, we'll be looking this 5G 6G communication from slightly different perspective, and we will be trying to see what are all the common things we can extract for this 5G 6G communication evolution. So I'll be giving an introduction initially about microphotonic technologies. And you know that because of the wide bandwidth capabilities, we can extend this to millimeter wave range of radars also. And I request all of you to think from a different perspective. I'll be seeing or viewing this from millimeter wave radar perspective, because I'm coming from a radar background, and you will be able to appreciate that majority of the things are common, whether it is communication system or radar system. So I'll be covering main photonic technologies that we can use in this 5G, 6G communication systems also, starting with RF signal generation, then various photonic-based up-down conversion methodologies. And we will also see in a previous talk, we have seen very clearly how very nicely Dr. Delma has explained about the ROF link communication systems. So we will also see how we can explore optical beamforming technology for the 5G, 6G applications. And I will also give an insight towards wide bandwidth applications, which are very, very essential for radar systems. Finally, I'll be mentioning about one more aspect, that is photonic-based radar receivers directly. Anyway, when I will go to that section, I'll be able to give in a better perspective. And we will also have a look, do we have to make photonic integrated circuits? Why? Is it a real necessity for that? Yes, answer is yes. I will come back to that. And I'll be concluding my section with the highlighting these features. So if we see the basic definition, I'm not going in depth of that. Basically, a study of photonic devices operating in micro frequencies and their application to micro and optical systems. And if we see, we can, it is having many advantages, that because of the significantly, it will reduce the size, weight, and of course, in previous multiple sessions, we could hear that it is going to reduce the loss factor associated with the RF signals. I can straight away tell you, where we deal with the RF signals 1 dB per meter, here we are going ahead with 0.1 dB per kilometer. So we are going to get an improvement factor in terms of the loss itself. And similarly, another important issue what we face normally in RF conventional system is immunity to electromagnetic interference. And as you go to the higher and higher order of frequencies, this EMI interference, that is electromagnetic interference, increases. I do not know whether you will be in a position to imagine a phased array antenna with more than 3000 elements. It is going to have immense complexity of cabling system at the back of the antenna, phased array antennas. So if we are in a position to use photonic technologies for the distribution of this RF signals, it is going to reduce the complete complexity of the phased array antennas, as well as the weight, which will reduce the driver capacity requirements for rotation of an antenna in our kind of applications, which I may not be able to explain to you directly. And similarly, the photonics enables us to do multi-functions because of its high bandwidth capabilities. That is, conventionally, we may be doing only for normal operation of search, track, and other detection and other things. But by using the same data, we can also do the imaging. That is the beauty of photonic technologies. Now, coming to why do we require this? Basically, I've just listed out. We will be preferring a single system for doing multi-functionalities with operational carrier frequencies, diversity in operational carrier frequencies, waveform, bandwidth, and superior phase noise, high resolution, frequency independent architecture. I want to dwell upon on the last point, that is, in conventional normal systems, if I'm operating with a particular frequency, for example, if you take in RF, you know that I told you that you may have to relate with respect to 5G, 6G communication. In the normal thing, if it is an L-band radar or S-band or C or X, we should have multiple levels of local oscillator signals. And similarly, when the signal comes back, we have to down convert this RF signals by using multiple levels of local oscillator signals and mixer stages. So each time when I do up conversion or down conversion with mixers, it is going to introduce noise in the signal. So there are methods which will directly down convert the signal from RF directly to the baseband. And similarly, we can generate directly the RF signals without the usage of these frequency dependent mixer stages and local oscillator signals. So anyway, I'm not going to explain that once again. So we always prefer these systems to work with wide bandwidth, waveform agility, carrier frequency agility, superior phase noise stability, high resolution, adaptive to environment. And similarly, if we are able to get the solution with a small size, that is the best thing. So, and always, we in the previous talk also, we have listened to this requirement of very, if we are able to get sensitivity and dynamic range with a proper, I was also asking her about the SFDR, which is very, very essential when we are transmitting RF signals or fiber links. So I just brought out what are all the major photonic technologies we can think about from a microwave and millimeter wave technologies. We can think about the direct generation of RF signals, its detection, distribution, and anyway, one point is may not be directly applicable here. That also I have included optical rotary joints. So I just wanted to I wanted to tell you where and all we can introduce the optical technologies, even in generation, detection, beamforming, and even in the signal processing also. We can bring the photonic technologies. So these are all the things where and all we can bring out the photonic technologies in radar communication as well as in our other communication systems. So the major advantages are it is going to be frequency independent. And another thing is we were hearing about MIMO radars. With the photonic based transmitter receiver configuration, I'm going to have coherent transmitter receivers where I can have multi-band of signals also. I hope those who are from the micro photonics domain, millimeter wave domain also, you will be able to appreciate this fact that in conventional systems, we depend upon this L band or S band separate, and we should also maintain coherency between the signals. So in addition to this, we don't require this. I already mentioned about this, no requirement of RF mixer stages and LO generation modules. And antenna, here we are trying to minimize RF front end, and remaining things, we can bring it to a faraway location. RF people will be trying to do the opposite. That is, they are trying to pack as much as possible nearing to the antenna, and only the data will be coming to a faraway location with fiber cable. So here the advantage is by keeping very less, only the antenna element, and the rest of the things, the RF itself can be carried out to a longer distance by using ROF links. And the rest of the processing also we can do kilometers away. With that, we are going to gain a lot of advantages over the conventional systems. Even if we are losing our resources, we will not lose majority of the resources. I hope you will be able to imagine that. And another thing what I wanted to tell you is it is going to have a very low distribution loss when we are going with the fiber optic link, and very high bandwidth and high resolution. I do not know how many of you are aware that by using optical technologies or photonic technologies, we are going to have the instantaneous bandwidth of the order of gigahertz. So it is not that we are able to get the signal back. We also will be in a position to do the imaging of the target also in our case. So similarly, photonic integrated circuits are really necessary to bring to a lightweight with a small form factor solutions. So it is mandatory. And I will just share with you, all these are applicable for 5G, 6G applications also. The generation, I will also map how it is useful in 5G, 6G applications, so that it will be in a better position to appreciate. So a simple method wherever we, the first thing people talk about the optical heterodyning by beating two wavelengths, PD being a square law device, we can generate the RF directly. So we are eliminating all other intermediate stages in the conventional method. So this is one example in which we were trying to do a lot of different types of analysis. These are, I am coming from an experimental background rather than theoretical this thing. So we are more focused on experimental studies and how far it is possible or to realize in practical scenarios. So I'm just sharing some of the results what we obtained. And the previous slide was showing about a situation where by beating two lasers, we can generate the RF signals. But in this case, I'm showing another one. There is a kind of laser. I do not know whether you have had a mode locking lasers. So what happens is we'll have a wavelength, we will have frequency comb lines. By using suitable comb lines, we can generate various RF frequency directly. So this shows that. And here again, this pulse laser is nothing but the mode lock laser. And by suitably by heterodyning suitably the wavelengths, we can generate different bands of RF signals. And similarly, we can generate RF signals by using the method of quadrupling. That is, by suitably adjusting the bias points of modulators which are used, we can generate the very high frequency millimeter wave signals with a very high bandwidth. What exactly I wanted to tell you is, if the input IF is with certain frequency and bandwidth, by using this technique, we can directly generate very high frequency and high bandwidth. So we were, in many occasions, we were trying to explore different methodologies. And I have already mentioned, when I'm going to get very high bandwidth, it is going to help us to have a better resolution for the for further processing. And this is another method in which we can do this same thing only. I have seen that in the previous talk, it was mentioned. I just brought out the block diagram, that's all. Here, the way, the conventional way we upconvert the original RF signal by using suitably selecting this laser wavelengths, we can also do the up conversion and down conversion. So this is another method for the generation of RF. And these are the some of the results we obtained when we were trying to generate 1 gigahertz from 100 megahertz, and when we were trying to down convert the signal from RF frequency to IF frequency. So this is the these are the experimental results. And another method for generation of RF is by using cascaded MSM. So by using multiple numbers of modulators also, we can generate the RF signal. So what I wanted to tell you over here is, based on the application requirements, we can select the methodologies for the generation of RF signals. And you can see that as we increase the number and the frequency of the input frequency, we can see we can get the more and more sharp pulses. So I just want to map, because you will be thinking I have brought out different methods for the RF signal generation, where it is going to generate in use in conventional 5G, 6G applications. So I just want to map so that you will be able to understand. In the first case, I'm not able to see from here. So in the first case, local oscillator signal as well as the IF signal are used, and you can see that the signals are the comb lines are apart with a local oscillator frequencies. And in the second method, both are combined, and then further it is used for the generation of RF signals. So what I would like to tell you is, depending upon the application, we can use different methodologies for the generation of RF signal, and the practical scenario is explained here. And I would also like to touch upon the distribution of the signals by using the photonic methodologies. Already we have had multiple explanation regarding the space division, multiplexing, multi-core fibers. So now I would like to tell you where it is used and how it is going to be useful. So when you are using a phased array antenna, even for 5G or 6G application also, you have to feed multiple number of RF signals. Each of the signals we can convert to optical domain, and we can use wavelength division multiplexing technology to pass all these RF signals through a single fiber, rather than taking through different coaxial cable in the conventional method, what we were following till today. So this is a total paradigm shift when we are changing from RF to optical domain. So these are these are some of the experimental results. Like in normal methods, we don't use all of you are aware that we are not using the conventional carrier frequency. We always use different kinds of modulation techniques from different perspective of advantages in the case of radar systems. So we have done a lot of experiments with different types of modulation. So this is one example in which we were trying to pass linear frequency modulated RF signal through RF links. And what is its performance? We pass this signal through the RF link, and received at the receiver end, we converted into IQ signal, and we do a lot of processing to see the performance characteristics of this signal. And similarly, we were also trying to see what is the impact of the fiber length. Is there any variation in the, because as far as our systems are concerned, any simple delay will be coming as a Doppler shift for me. So it is going to mislead the target. So all these parameters are very, very important. And this is with continuous wave signal, and the down is the envelope of the signal, in which we were trying to see whether any signal variations are there. And similarly, we also conducted multiple experiments by using wavelength division multiplexing technology. So if you go with 5G, 6G application also, you will agree with me with the fact that it is not only RF signals. There are a lot of synchronization signal also should be transported. So what happens is we have to see when we are doing the wavelength division multiplexing with RF along with the digital signals, is there any effect on the receiver end? If it is going to affect our signal, there is no point in passing through a single fiber. So all this analysis have been carried out like by using different types of RF signals, then digital signals. And here, again, I would like to map with respect to 5G, 6G application, the same things are used in communication system also. Only thing is, the frequency which is used is differing from what we use, but the bands are same in certain cases. So whatever is applicable with our radar systems is also applicable for communication systems. Now, another important field where we can apply this microphotonic technology is optical beamforming. You all will agree with me that if we are trying to form the beam using the phased array antenna in the conventional way, it is depending upon the bandwidth of the signal, there will be an effect called beam squint. In the case of when we are going with the optical solutions, this delay can be easily implemented by using true time delays, which is independent of wavelength of the signal, or which is independent of the frequency of the signal. So optical domain solutions are far, far much better than our conventional RF solutions. So here we have conducted multiple experiments by trying to introduce the delays, and we were trying to capture the signal at the receiving end, the RF signal, after introducing the delay, and we were trying to form the beam. Again, I'm putting a slide for you to map this technology with 5G, 6G applications. So the same thing is happening. If you see here, it is nothing but here you can see that each of the signals is first converted to RF. Then after that, it is passed on to optical beamforming network, where delays are introduced. Further, it is multiplexed and passed on to multi-core fibers. And then again, it is going to the other end, antenna side, a PD is there. It will convert back to RF and further transmitted through the antennas. So what I wanted to convey to you is whatever is applicable in normal conventional radar systems, here also same thing is reused. So you can map that. I'm not going in depth of that. And similarly, as the instantaneous bandwidth of the signal increases, the resolution is going to increase, and that will help us to do the imaging aspects of the target systems. So this is a typical case which was reported with a 4 gigahertz signal, which is operating in the range of 22 to 26 gigahertz. We are able to see the target in a better way. But the problem here is, if you are using the conventional phase shifters in your antennas, the phased array antennas, there is an effect called beam squint, which since these phase shifters are depending upon the frequency of the operation, that bandwidth, bandwidth of the signal. So in order to avoid that, we have also developed a typical algorithm in the digital domain to compensate this. Even if you use conventional phase shifters, when the signal is received, we can do this compensation in the digital domain. But exactly, again, here, if I'm looking at this place, if I'm trying to steer the beam in 30 degrees, because of this beam squint, the signal will be 30.1. I'm just exaggerating for you to imagine. But this effect cannot be afforded in a radar system. When you are using in the conventional phased array antennas in any communication system, this cannot be accepted. So here we try to develop an algorithm which will do the correction in the digital domain. So what is the, here you can see that the original pulse compression output is represented with red color, and one is green is without with correction, and black is without correction. So you can see the impact of beam squint when we are using for high bandwidth applications. And similarly, when we are trying to form the beam in a particular direction, if we are not, again, due to the beam squint, there will be an error in the beam formation during the reception of the signal also. So this also should be considered while when you are doing the echo signal processing. In communication system also, this should be taken care, otherwise it will come as an error in the signal. And this is effect of the bandwidth is explained here with the 2 megahertz bandwidth, and this is with 400 megahertz bandwidth. You can see that in high bandwidth case only this beam squint effect is predominant, and here it is not predominant. When it is narrow band, this effect is very not predominant. And this is another example in which, as and when the higher and higher instantaneous bandwidth we go for, the resolution of the signal also increases. Because of that, we will be able to do a better imaging of the target. And this is another example in which we were trying to, after the signal is received, we should be in a position to directly detect the signal from RF. That means directly the RF is converted to IF signal. So here we are trying to use a pulse laser as the input, and this particular hardware setup could be realized with the help of private partner. He is also present here. With the support of him, we are able to do this, and we try to input the RF signal and the respective IF signal we could get back. And here the point over here is whether it is millimeter wave or RF wave, we can get back the baseband signal or IF signal directly. So this is going to drastically reduce the hardware complexity. So this is another experimental setup which we have used for filtering the signals, especially in communication systems. Since RF and digital signals are involved, we have to multiplex both the signals, and we should be in a position to segregate the signal at the receiving end, whether it is RF or digital. That also we were trying to do multiple experiments with a different type of signals. This is with NLFM. Maybe I'm not going here also in depth, because in certain cases we use NLFM and in certain cases we use LFM. So all these signals are depending upon the operational requirements. So we had to do lot of experiments with different kind of modulation formats. And before coming to an end, I would like to tell you that again, when we are using the commercially available components, it is going to increase the size, especially the swap. the size, weight, and power swap. So because of that, the systems will become bulky as on today, since the technology is not yet to be matured in certain field. So we have taken a lot of initiative to develop all these components indigenously within our country. As Dr. Deepa was mentioning, some things are done. We have already initiated in the communication domain. Same way, we have initiated a lot of activities to develop all these components indigenously within our country. So tomorrow, we are quite sure that with indigenization of these components, we'll be able to make our systems much with a lesser complexity, lesser weight, low loss, cable, RF links, everything. So I just wanted to tell you that here the main aim of this, my session was to see 5G, 6G communication system from a different perspective, from a radar perspective, because most of the technologies are common, whether it is a radar application or a communication application. So I'm quite sure that with the advancements in this MWP or millimeter wave technologies, along with the digital technologies in the coming years, it is going to enhance the performance of futuristic communication systems. So with this, I would like to end my session. Thank you.
Thank you, Dr. for the talk. Any questions?
Line width of laser as on day, but maybe 200 kilowatts or 300 kilowatts. Yes, heterodyning two laser to generate RF. Our resolution is getting low. How to address it?
Trying to realize this, we are not going ahead with conventional network. It should be very, you are rightly mentioning, we have to go with more to get the required phase noise, especially in the case of radar systems, and the jitter performance. We have to go with mode lock lasers with suitable jitter factors.
Even with mode lock, you should not be able to go below 200 kilowatts at all. So your Doppler, how you will extract that Doppler with so much of a large line width?
Yes, it has been already, I may not be in a position to tell you directly, but it is verified. It is possible.
TTD, you are saying it's a frequency independent. Is it? We are talking large bandwidth, 5G, 6G. It is not frequency independent. It is definitely going to be on frequency dependent because we are talking large bandwidth. Squint will come. You cannot avoid it.
I will tell you. In the I didn't because the audience are here. I've seen that it is diversity is there. That's why I didn't go in depth of that. Actually, most of the conventional radar systems operate with narrow band. So the phase shift normally we are putting it is, if you want theoretically also I can tell you, it is nothing but 2 pi by lambda into d sine theta, where so lambda is directly coming over there. So it is dependent, and the moment when we are going for high bandwidth solutions, it is going to affect, because normally we will not be in real time. We cannot change the frequency when it is of the order of gigahertz and 500 megahertz. In those systems, these errors come, and especially we have to use anyway. Since you asked that question, I will only superficially I will be able to tell you. Especially for synthetic aperture radars, we have to go the band. We have to go with a bandwidth of the order of hundreds of megahertz or gigahertz. So there, this is very prominent, and we use a different technology. So in those situations, this optical beamforming is going to be where delta T is nothing but d sine theta by c, which is independent of lambda.
Yeah, actually, it will only minimize. It will not completely eliminate it.
I know. Here also, I would like to tell you, we are trying to develop this beamforming, optical beamforming. As communication things are coming forward, same way we are also evolving in this field in the microwave and millimeter wave technologies. Optical. Photonic technologies. I am not telling about conventional millimeter wave or RF technologies. I'm talking about microwave and millimeter wave photonic technologies. It's a new area.
Oh, it's not a new, it's a very old area.
Any other questions from the audience? So if not, let's thank the speaker again. So we've got the memento for the speaker.
Because since we are doing for the first time, the way we are in the country, we are doing for the first time.
Thank you. I now request Dr. Bijay Krishna Das, Professor at IIT Madras, to join us on the stage for presenting a token of appreciation for the session chair. Thank you. We have come to the end of today's program. Let me take this opportunity to thank each one of you for gracing today's session with your presence. We have arranged a dinner around 7. Meanwhile, you can have a glance at the exhibition hall. Please note that for tomorrow's session, we will be meeting in the auditorium at D7, the floor just above this, where we had our morning sessions. Please be with us from 8 a.m. for the next set of exciting sessions as a part of Day 2 program. Off for the day. See you soon. Thank you.